सर ये फुल स्क्रीन कर दूं?
थोड़ा सा डिले है ऑन करके ओके
देखने के लिए भी है कोई चीज तो लोग क्या बोल रहा है वो सुनते नहीं है, वो थोड़ा
देख लेते हैं।
एग्जीबिशन गैलरी वही जस्ट के पास
Morning. Good morning.
Good morning, sir.
Is Dr. Alok Ray is there or not yet come? I think not yet joined.
Ata is I'm
Yeah.
already in the dais. Just I think they have to put on the laptop. The laptop to already on here. Yeah, I'm already there. We have to start sharp 9 o'clock because
Okay.
because as you have decided 15 minutes for the presentation, 12 minutes they will give a bell for 3 more minutes, and 5 minutes for the question answers. Okay.
Okay.
And after that, of course, we are planning to meet. Another parallel session is going on. So after that, maybe 11:45, we'll try to have a meeting of all the judges in one common platform to take a decision.
Yeah.
And yesterday, I have sent a mail to you that.
Yes. I have taken already.
Please take a printout of all the, or maybe keep it to you. Okay. So please
Yeah.
probe it properly and let us see. Will. Okay.
Yeah.
I think आपका voice तो clear है. Only I think Ghosh, Professor Ghosh has joined from ISR Kolkata. He has joined. Other all are online. I think Sunil Verma from RRCAT. RRCAT. Okay. Maybe we can start.
हो गया वीडियो हाँ ठीक है हो गया
First speaker is there.
Yeah, good morning.
Okay, good morning, Dr. Verma.
Good morning, everybody.
Yeah, Saturday is a little bit tight.
So good morning.
I think Professor Ghosh is there. Ghosh.
Good morning and welcome you all
Join online.
in NLS-30, last day, session 13. So we are going to start the thesis presentation now in auditorium A. So we request all presenters to be online. If somebody is not connected, we will go to the next presenter and your turn will come in the end. So you have total 15 minutes to present. After 12 minutes, first bell will ring. After 15 minutes, last bell will ring. So please wind up the presentation quickly. And the control will, after 15 minutes, go to the judges for question and answer session. So now I request the first presenter.
So we have 15 plus how many minutes for question answer?
5 minutes.
5 minutes, okay.
Hello.
So now I request the first presenter, Mr. Amit. to start
Yes,
now.
sir.
Mr. Amit, please start.
First of all, good morning all, and thank you NLS for giving me opportunity to speak on my research topic, that is phase extraction of optical interferometric signal based on improved time frequency method with application to high standard measurement under the guidance of Delma and co-guide Dr. T.C. Koshit. So what is the outlines of my talk is, I'll just briefly give some introduction of the interferometric technique, what is being applied in my research work, and briefly touch upon the literature survey. And then I'll go through the one of the techniques that is called the phase stepping technique and how it has been used for my applications. And then subsequently, I'll touch upon the continuous wavelet transform method and pseudo-equilibrium distribution method. Whatever the theory has been developed, finally, the last chapter I will discuss upon the application of free surface velocity measurement in high standard experiment, and finally I will conclude. So before going to this my research objective is phase extraction of interferometric signals. So interferometric technique is a superposition of two electromagnetic waves. So that area of application starts from the astronomy to shockwave physics. When I say astronomy, you can say that on the world's tiniest measurement like gravitational wave detections is possible only through this interferometric technique. And various applications area measure physical parameters are there, like somebody wants to measure the displacement, strain, velocity, surface profile, all of such measurements may not be possible in physical sensor based, because so many limitations are there. And the advancement of this laser based technique has solved those problems. And I will show that some of the experimental techniques that is not possible with the conventional technique, but possible with this laser based interferometric techniques. So moment I say interferometer, the first things my keep into the minds is the Michelson interferometer, the most basic form of the interferometers, where the light source is split into two parts and going to the two different paths and combined again, and it is being detected through detectors and on any either photomultiplier tube and oscilloscope or any kind of CCD camera. The main principle of this is when the lights travel in the two different paths, if the path difference takes place, and that creates a phase difference, and then it forms the interference pattern. So interference pattern ultimately carries the information whatever the creates my path difference. It may be due to the change of this one of the mirrors, it may be due to the in refractive index changes in this path. So it doesn't matter how it happens, but the fundamental things is happen that when both are in the same phase, then it will create the constructive interference. When it is out of phase, it will create a destructive interference. And the phase and frequency, this is the governing equations when it is a two electromagnetic wave are superimposed. These kind of equations will form, and the phase or frequency of this information carries my physical parameters, whether it is strain, whether it is displacement, whether it is velocity. So what happens? So main important parameters is the source, because forming an interferometer does not say about what kind of source should be there. But problem is if it doesn't have any coherent and monochromatic, then what will happen? The source itself is changing the phase. Then I will not able to know whether it is changing due to my physical parameter or due to my source. So coherent lens and monochromatic, this is the most fundamental property that should hold, and undoubtedly laser has solved that problem. So when I say the basic velocimetry, it's the measurement of velocity with the interferometric techniques. So my research objective that when a target when when a flyer is moving a very supersonic velocity hits a target material, then a shockwave starts propagating. When the shockwave starts propagating and it reaches the outer surface, I wanted to measure that free surface velocity, because that measurement carries a very important mechanical properties of this target material. So what is the how does it happen? It may happen due to these displacement interferometer configurations, or it may be due to these velocity interferometer configurations. In displacement interferometer, you can see the velocity is proportional to the frequency of the fringe signals, and this velocity interferometer, the velocity is proportional to the phase of the fringe signals. What happens in this particular case? The target, the light coming from the target material, it has two paths in two different. Some delay has been proposed. So by placing this delay, it will create a f the change of phase is proportional to the velocity information. So in these conditions, we will have some optical differentiation is taking place, so that the frequency is very less. So low bandwidth instrument can be used, but in this case, very high bandwidth instrumentation has to be used. But but model of the study is that I have to either extract the frequency or phase of the interferometer signals. So this is my research objective. So I'll quickly go through this how we have solved this problem in various chapters. So literature, when I say the literature chapters, lot of literatures available in the context of fringe analysis. The entire topic is called the fringe analysis, means how to extract the phase or frequency and others any higher derivative parameters. So most of the is literature available in the context of digital holographic interferometry, fringe projection interferometry, and digital speckle pattern interferometry. So most of the literatures are divided into two parts. One is called the time domain approach, that is based on the phase shifting method, and the frequency domain approach. Most of the techniques are short time Fourier transform, continuous wavelet transform, and many more. So, and finally, I have also touched upon the what is my application and how this gap is there, and how how some novel analysis technique has been applied. And I would say this one of the editorial topic that is based on is optics and lasers in engineering, and this fringe analysis premises perspective. This has elaborate literature, more than 220 literatures are available, totally focusing on this topic. So this one paper is very useful for any other researcher in this domain. So when I say this first chapter is phase traction techniques. So when I say the phase traction, this is a temporal domain, one means time domain of this. So I have this governing equations. So one equation, because I have tested the phase from these one equations, there is a unknown parameters is 3. So it is not possible. So how it can be solved? I will generate another phase by putting an phase shifter. So I can create another phase that is shifted by pi by 2. So if it is all this this DC term is same, then I would have been a very simple equations. But practically these two equations is happened, but exactly pi by 2 is sometimes not possible. So there is an error angle. So when I combine these two equations, I can find that phase of the signals, and that is given by these mathematical equations. So I1, I2, my two measured variables, but I have another five parameters: A1, A2, B1, B2, and epsilon. These all 5 parameters can be obtained by fitting an ellipse, because this equation forms an ellipse of these equations. So I have and another problem is that this equation, that arctan function is also when it crosses this 2 pi, again it has come down to its initial position. So that the phase has to be undamped. So I have developed my undamping algorithm. Also there is a commercial available package, but my algorithm is more robust. And then finally I have done some experiments, and this is other Michelson interferometers. The laser is splitting in the two parts, and it is reflecting 2 mirrors. And one of the mirrors I have attached piezo vibrators. So I have given a sinusoidal supply to this piezo, is the blue color. And due to the supply of the sinusoidal voltage, this piezo start vibrating. Now when the piezo start vibrating, that two interference fringes are generated in two quadrature formation. This is the polarizing beam splitter that will create a two quadrature formations, means one is sinusoidal and another is cos functions. So from these two measured signals, I use these functions, then I unwrap it, and then finally this is my governing equation. I can expect this is my displacement, and this is before that I have fitted my data in ellipse, and that will generate my major axis, minor axis, and rotation of the ellipse. This all parameter has been fitted. So it is more accurately, it is plotted. So next chapter, I will cover this continuous wavelet transform. This is a frequency domain approach. Earlier, I have shown this. My experimental data is a continuous. Each and every time this frequency is changing. So when I say continuous wavelet transform, before that, I would like to say that from temporal to frequency domain, the Fourier is the only options. The moment I give the Fourier transform, I lost the all time information, because my application is each and every instant of time I want to measure the frequency of the signals. So immediate solution is that short-term Fourier transform. Okay, I am not able to give that entire time in one shot, but I can do this Fourier transform very small window. If I do that, I can that immediate solve the problem. But short-term Fourier transform, it has some own limitations, because when I say that once I choose the window, that resolution is same. So sometimes we get some information loose from the short-time Fourier transform. So immediate solution is the continuous wavelet transform. So what is the beauty of these things? The continuous wavelet transform, the basis function itself is changing. So it is localized. That unlike in Fourier basis function, that is a perpetual for sine functions. But when I say wavelet basis function, it starts sometimes and it's died out. So this kind of if I take the inner product of this function to any arbitrary function of my signals, I can get some kind of localized informations. So it's almost similar to the Fourier, but only thing the basis function is changed. So there is various different types of wavelet has evolved. Like unlike Fourier, this is only sine and cosine basis function is there. But in wavelet transform, so many basis function has been evolved for various applications. So once I take this inner product of this my signals with this basis function, I get some kind of coefficients. These coefficients, when these two function matches, this will be maximum. So indirectly, I know that the frequency and phase of this wavelet function. From that, I can get back to what is the frequency and phase of this my functions. So this is the basics of the wavelet. Now I can say that two functions are there in wavelet. One is the A and another is B. B is shifting from my one position to another position, and A is scaling. Once I say the scaling parameter, that means it is a compression and expansion. So different type of frequency can capture on the basis of the different scale parameters. And when I see the shifting, it is time shifting for different space of the signals. But the moment I say that this is a very good time localization because its activity is very narrow within this time range compared to this red one, this is spread in wider time zone. But okay, sir, I quickly finish. But the problem is that frequency domain, it has a very spread in frequency. So reverse equation is problem is there. So which wavelet should I choose? I have used the modulate wavelet because it has its own easiness. But only problem is that this wavelet has sigma and omega 0 two parameters are there. I try to optimize that parameters. Initially, I have proposed that theory. But optimization only not only solve that problem, there is a linear discontinuity is obtaining. Then I have gone through the simulations work. This is the known phase and known frequency. And from there, I try to get that what can I get back to marginal frequency? And for that, I have used the reassignment techniques. And I termed it reassignment modified program, and nobody applied in combination of this wavelet modification as well as reassignment technique in applications. So this was my simulated data, and this is my proposed theory, and it is very much matching with this expected theory. Finally, I have applied my experimental data with these techniques, and finally we get this velocity profile as well as displacement profile, and very much accurately. And this was published in one of the journals. And that chapter, next chapter, this is also the frequency domain approach. This is the pseudo-inequality distribution method. And in these techniques, what happens? It is not possible to apply direct Fourier transform, but I can take the instantaneous autocorrelation function. And if I take this Fourier transform of autocorrelation function, then I will get back to the power spectral density directly. And it has some own limitation but it has some very nice mathematical properties. I have applied these Cohen class signals. This is my simulation profile because most of our application we found that a lot of polynomial function is happening. So I generated this polynomial function, correspondingly I generate this fringe, and I try to extract the fringe of the signals. And this is very nicely matching with this technique. And finally, I do this, conduct this experiment, and I develop this, whatever the simulation data, I try to fit into this, my experimental data, and this is my experimental data, and both are matching very nicely. This work published in Optic. Finally, my application is to free surface velocity measurement in high standard experiment. This is a gas gun facility is our laboratory where very high velocity is moved to the gas propulsions. So it may be any another thing, chemical explosive, laser, and electromagnetic launchers. So the two interferometric mode has been studied. One is the velocity mode that I already told, and another is the heterodynamic technique, that is a displacement mode or PDB. And if I say the ideal conditions, my phase is like that. But in practical conditions, I have this equation, which is again a form of ellipse equations. So I have gone through this detailed study of what kind of ellipse should I fit. Should I choose the standard 2 minutes, sir? 1 minute, sir. Should I go to this? Yes, sir. Should I go to this geometric method or algebraic method? Then I have gone through this details investigation. Which ellipse should I fit? Which mode, sir? Then I propose that Bookstein of the algebraic method initial condition should be chosen, and then I will apply this Gauss-Newton algorithm, which is giving the best result. And finally, I have conducted this experiment, and this is our velocity profile, which is much more accurate, and we can exactly fine-tuning the different signatures of the signals, which is very, very important for extracting the various mechanical properties like dynamic yield state, spot state, and HEL, etc. And finally, I've also used this technique.
The conclusion slide, please.
Yes, sir. And this work is also published in one of the journals. So I have shown this, the phase shifting algorithm I have used, then continuous wavelet transform I have used, smooth pseudo-inequality distribution has been used, and finally this proposed theory has been applied to
question.
Yes, sir.
Professor Tata.
Sorry. Yeah. I just want to two questions first. How do you mentioned in your thesis high strain rate, but yes, nowhere the strain rate dependence, high or low, that is not seen in your any of the chapter.
Sir, actually last chapter it is there because
that is only your verification. right? You means,
Yes, sir.
yeah.
When I say the high strain rate, because this you can say this is the velocity profile. So the slope is giving a very important parameter that is called the Hugonot elastic limit. So strain rate, when I say the high strain rate, yeah, if I have to find the strain rate of this velocity profile from these informations, and that is also plotted in my thesis. So that gives a very important mechanical properties of finding of this. If I don't able to find this is properly, so it will give a misinformations.
No, the
So in that context,
the strain rates are applied on what? One of the mirrors, right? The velocity different.
yes, sir.
How
Actually,
you
sir,
what is the relation between strain rate and velocity?
Sir, actually, sir, whenever I showed that the mirror, so it is in experiment, it is not applied to direct mirror. Just let me go to this.
No, you can just explain to me because it takes time. Yeah.
Sir, from the velocity, if I integrate this, I can go back to the displacement, and from the displacement, I can find the strain rate and strain and strain rate.
Okay, but when you do a Fourier transformation, one is the
Yes, sir.
you record the fringes intensity
Yes,
as
sir.
a function of path difference. One.
Yes, sir.
Other one is frequency. Now,
Yes,
how
sir.
do you? What is the you do only finite time domain or finite displacement domain? Okay.
Yes, sir.
What will be the errors which are involved when you convert into the Fourier transformation?
Yes, sir. That's why that when I say this, the fundamental errors come from these uncertainty principles. Because I have shown that this kind of signals, or not only Fourier transform cannot solve this problem. Because Fourier, I lost all the time information, so I have to go to a short time Fourier transform and otherwise continuous Wavelet transform. Moment I see short time Fourier transform, the window decides what is.
FFT will take care of the doing things fast, but
Yes, sir.
I'm asking you the finiteness. One is the delta path difference resolution. Other one is the integral 0 to infinity.
Yes,
the infinity
yes,
replaced by a finite. What are these two imposes on your final result?
Yes, sir. When I do this Fourier transform, the number of because we have a finite data, so this whatever the number of data points are there, in frequency domain it is delta total time divided by delta f. If delta f is inversely proportional to the that step function I am using. So that decides my resolution of this frequency domain.
Okay. My last question, how did you generate this velocity high strain rate experimentally? Because you said you did.
Yes, sir. So
How
this
did you do?
experimental, so this experimental generation is there is a different methods. Chemical explosive, I can propel that target
No,
through
what
this
did
chemical
you do?
explosive
What
gas.
did you do? Yeah.
We have used our gas gun facility. We have a compressed gas is over there. So once I release that gas, it propels a projectile in a supersonic velocity, moving more than 500 to 1 kilometer velocity, and it hits a target material. So I have a laser probe over there, and when the shock high strain rate loading is there, then outer surface starts moving. So I have a Doppler shift of the incident laser and the reflected laser. So that Doppler shift ultimately takes care of this velocity information of these target materials.
Okay,
So
fine.
we are
Officer
having
Ghosh,
gas gun facility now.
Thank you. Right.
Officer Ghosh, then
If
Dr. Verma.
so this is Nirmal Logos here. May I ask a few questions, one or two? Hi, can you hear me?
Yes, sir.
Hi, can I ask a couple of questions, quick questions?
Yeah, please.
Yeah. So this is more basic. So as you see that when you write the interfering signal, you write AT, and then you also write the phase factor phi t, right? Both fluctuate as a function of time.
Yes, sir.
How these two differently, like amplitude fluctuation and phase fluctuation, will affect your result when you try to extract phase?
Yes, sir. Actually, this amplitude, that A of t, that is called the DC term, that fluctuation is absolutely very slow with respect to the phase and frequency terms. So some people, what happens? Some people has done this. They have used some kind of filtering technique or data acquisition in kind like coupling of the capacitors. They remove these DC terms. But in my case, I have not removed this DC term. I retained that term, but I have fit in Ellis fitting. From there, I have derived those terms.
Yeah, but if it is fluctuating as a function of time, it cannot be DC, right?
Absolutely, sir. But if it is compatibly with respect to this frequency, you can say this.
Okay, can you listen to the question first? So my question is
Yes,
that
sir.
why do you think that the amplitude fluctuation and the phase fluctuation of the source can be different? Right? So do they have different origin? Are they both related to the coherence of light? Understood. So amplitude
yes, sir.
and phase fluctuation, they are actually related to the coherence of the source, right? So if you take a perfectly coherent monochromatic source, they are just like fixed, right? A and phi are constant.
Yes, sir.
So why do you say that the amplitude fluctuation will be slow and the phase fluctuation will be faster? Is there a physical basis of this discrimination? And the second question is that, so this role of these fluctuations, when you do any interferometric measurement, so role of these fluctuations in the Fourier analysis is quite well understood, right? So we know that how it will affect. But you have also used wavelet analysis, right? So,
yes, sir.
So in terms of coherence, how does that affect your wavelet analysis?
Sir, in terms of the coherence, because we are using this laser, it's a very long coherence length. So in our applications, it is remain coherent, and
just a quantitative answer is important. You know, so suppose you have a coherent source, but it gets reflected from somewhere, it will lead to some fluctuations. The question is, Fourier, the fluctuations on the Fourier is better understood, but how is it understood in the context of wavelet? Because in wavelet you do over a very finite time or spatial scale, right?
Yes, sir. Yes, sir. So, sir, that's why the beauty of this wavelet comes into these pictures. Definitely, nobody can beat the Fourier transform, because that is the most frequency domain. It is the most sharp and in frequency domains. So, absolutely, resolution is very almost close to zero. So, in frequency domain, the Fourier is the best. But the problem is, I totally lost my time information.
So that is
so there I have to do
that we know.
That's why wavelet.
That we know.
Yes,
that is why people use wavelet. That in Fourier you only do a Fourier transform, you know the power spectrum only. But there are
only
the
power
problem
spectrum
is that the fluctuations. So that the wavelet is of course more prone to those fluctuations. So how do you take care of that?
So that fluctuation in my case, that DC shift and that fluctuation is very slow.
Unless you have a proper idea, quantitative idea, how can you say that in your case it was not there? What do you expect? Let's say I have a fluctuating function like A and phi. So how do you how does it affect your Fourier transform and how does it affect your wavelet transform? Can you give us an idea?
Yes, sir. Yes, sir. So that whether it is changing in the amplitude modulation and frequency modulation. If I do the Fourier transform, I will have the bandwidth. So it will reflect in both coming to that.
That is well understood. But in wavelet, how does it affect? That is what I want to know.
So even the similar case of wavelet, it is also there. It is not that
how do you quantify that? So in case of Fourier, we know that is what monochromaticity and coherence are related, right?
Yes, sir. Yes,
sir. Yes, sir. How do you quantify that?
I said only wavelet, that quantification comes from this mother wavelet. How do I choose this mother wavelet, which is have a very narrow bandwidth?
Okay, I think I am done because time is short.
Dr. Verma, you have any quick question? Quick question, please.
Did you hello? Did you do any error analysis of your results? I mean, I didn't see that.
Yes, sir. Actually, when I say this velocity profile, I have always mentioned the velocity with the percentage of uncertainty. So that uncertainty has been calculated from my experimental data. Because when I say this ellipse fitting and everything I have carried out, so I have found out the total overall uncertainty and I put it. When I say this Fourier transform or wavelet transform, I find out the uncertainty from.
So what is the percentage? Give me the number.
Sir, it is varying. So some of the experiments I have achieved 1 to 2% of the uncertainty, and sometimes it is less. So this kind of
one more thing. Uncertainty you are saying is the same as error analysis. That is what you mean?
No, sir. Measurement and uncertainty.
I'm talking about error analysis. Fine. So don't talk about the uncertainty.
Okay, sir. Error analysis in details I have not performed in this particular thesis.
And second thing was in all your presentation, I was expecting that you would show some experimental interferograms and all those things, but that I didn't see. Because, right, because most of the thing was computational, and in computations you have to actually show validation and error analysis, and that is missing.
Okay, sir, this is my experimental facility, and
no, that is fine. These are all schematic. Fine. No, I am just pointing out that when you are giving a presentation, and you must include the experimental results. Fine.
Yes, sir. It is. Finally, I have actually shown last slide. It was there in experimental.
We can't, sir. We have to move to next. Time is a little bit problem.
Okay, so I think I am done.
Sir, these are the fundamental property I have derived from these equations. So this is the experimental data of ammonia.
You should have shown this in your presentation.
Actually, it is last slide, so I was able to speak on that.
Move to the next. Dr. Sujita Sinha will move to the next.
Okay, fine.
Okay,
thank you.
Thank you.
Next one will ask question. Okay.
Okay, no problem.
So our next presenter is Mr. Nagaraju. Mr. Nagaraju, are you there? Yeah, please start.
Please, hello sir, good morning all. Hello?
Yeah, please start. You are audible.
Yeah, is my presentation visible?
Yeah.
Yeah, thank you. So, good morning all. Thank you for the opportunity to give my talk on this NLS-30. Today, I'm going to talk my thesis on dynamics of confined laser-induced ablative plasmas and shock waves. This work done under the supervision of Dr. Prem Kiran in the University of Hyderabad. And 1 minute. So this is the content of my talks, where I will give the brief introduction and a glimpse of my thesis work. And my work mainly done on the plasma confinement methods. So these are my working chapters, where I will use different confinements of the air plasma and metal plasma. And then I will give the thesis summary. And in the dynamic states of matter, when the matter is compressed with high, they can be two ways. One is static way, another one is dynamic way. So in dynamic way, we are using high power lasers to compress the material. So if you see the temporal and the spatial time scales, where different techniques are used to compress the material, the laser can be used as within short time, you can get a gigapascal pressures with within nanosecond or less than that. But the main problem here is the efficient conversion of this optical energy to the kinetic energy or the pressure, where pressure is a function of the intensity and the wavelength of the laser. So mainly my aim of the thesis is to lay a roadmap to the laser-based millimeter shock tube. Why we need a laser-based shock tube means if you see the conventional shock tube, it will use space and power consumption, and it will generate very less shock pressures. But in the laser-based shock tube, where the laser pulse is used to create a intense high-pressure plasma, and the plasma and subsequent shock wave will travel inside a microtube, which acts as a test section. So for our simplicity, we have divided the problem into 3 stages. The first stage is the generation of the efficient plasma inside a confinement method, and there is second one is that the propagation of plasma and shock waves inside a tube. And by optimizing these parameters, we will go to the final stage of the laser-based millimeter shock tube. So the main mechanism involved here is that generation of high pressure plasma in the confinement and the evaluation of the plasma and shock waves inside the tube. But there are challenges here, that how to generate efficient plasma in the confinement, and how the evolution dynamics looks inside a microchannel tube, and how to optimize the laser and tube parameters. So the whole work is done using the visualization technique, which is known as shadowgraphy, which is easy to align, and the difference in the light intensity is proportional to the second derivative of the refractive index. So to give you a glimpse of my thesis, so when the laser is focused, the plasma and subsequent shock wave are formed, and while freely expanding plasma and shock waves, if you confine based on the laser propagation, you can have a confinement. The axial confinement means you can obstruct the expansion of the plasma or the shock wave along the laser direction, and spatial confinements perpendicular to the laser direction, you can confine the plasma and shock waves. So in the axial confinement, there are another two methods. One is fluid confinement, another one is the solid confinement. The example for the fluid confinement is the two interaction of two plasmas side by side, and the example for the solid confinement is the laser-induced blow-off from a thin foils. And the spatial confinement example is given as a plasma confinement, spatial confinement of air plasma inside a rectangular tube. And by using this confinement technique, there is some applications we are examining. That is visualizing the shock waves inside the material, which is related to laser-induced laser shock cleaning technique. Another one is to demonstrate the millimeter size shock tube, where you can see the laser generated shock wave inside the tube. Still, we are optimizing this thing. And this is the experimental schematic used for generation of the plasma. And the helium neon is used as a probe here, which is expanded to 43 mm beam. So and we are using the ICCD device to get the temporal technique of the temporal evolution of the plasma and the subsequent shock waves. And if you go the first chapter, working chapter, discuss with the one of the confinement. The first one is the double pulse configuration, where based on geometry, you can divide the double pulse configuration into different things. Here we are our approach is in the counterpropagation direction. So in counterpropagation direction, two lasers are focused side by side, collinear to each other, where the plasmas will be formed and interact with each other, generating a stagnation layer at the center. And the shock wave from the one plasma source travel through the other source, which will give the discontinuous in the plasma source, other plasma source. So the collision of the two plasma sources depends on mainly the separation distance and the ion-ion mean free path, which is indirectly dependent on the plasma velocities. So we have studied using separation distance and the energy ratio, how the dynamics will change here. If you see the source separated by 1 mm distance, this is the single source, single plasma and shock wave evolution with temporal evolution. And if you see the side-by-side evolution of the two plasmas, so initially there are two plasmas are visualizable, then it will merge it into a single plasma. As the energy increases, there is a discontinuity at the interaction zone, but it's not completely dividing. So it still acts as a single plasma and the shock wave. So these are the self-evident studies we have done. And from the, if you increase the distance between the two plasmas, what you observe is that the plasmas will interact with each other and create a stagnation layer, but the plasma shock wave from one higher end source plasma will create discontinuity in the lower source, lower plasma. And this is evident by the self-emission studies also here, where you will get the jet-like formation from the plasmas, both sides in the equal sources, and unequal sources in the smaller energy plasma, you will get the jet-like. And this is the collisional parliamentary example where the jetlet formation is done if you have unequal sources. And the jetlet evolution is also dependent on the separation distance between that. But for higher energy sources, as soon as the plasmas are generated, there is a discontinuity, that is a jetlet formation, which moves in a linear velocity. And this is the highlights of my work, which gives rise to two publications, and one more we are going to submit. And next, coming to my second chapter, where we have studied the laser-induced blow-off. First, this is when the laser incident on a material, bulk material, you will get a plasma and shock wave, which is travels opposite to the laser direction, which is known as ablation. And if you have a very thin film, in incident laser incident on thin film, you will get a blow-off plasma. But the thin film is very small, so that because of the laser pressure, it will wobble. So to confine this, we use the confined libo, where the glass slab is used as a support to the thin film, and the plasma, ablative plasma is created, and the blow-off plasma is created right side of the film. And this thing will mainly, the pressure in the blow-off region mainly depends on the acoustic impedance of the material and the intensity we applied here. So we studied both using different materials and different focal spot. So here we have used two kind of focal geometries. This is because when the blow to increase the blow of shock velocity and increase velocity, we have to increase the optical and conversion of the optical energy to the material. So we have used a focal shifting of focal plane shift where it will generate high spot rate, high beam laser focus spot on the material, and that increase the blow of velocity. If you see in the exact focusing condition, there is very small blow off occurring here right in front of the film, and there is a ablative thing. But when you change the focusing condition to f1, that is 1 mm, move 1 mm by that, you will see that the blow off is drastically increased and getting a cone-like structure here, and there is negligible ablative shock wave. And in the F2 also, you will get more cone-like structure in the blow-off region, and you can minimize the ablative shock wave here. So in the same case, you will use for higher energies also, the same thing is observed, because at higher energies, there is a chance for the glass damage. So we can avoid the glass damage efficiently by using this, changing the focusing condition. The study is further applied for micron level and nanometer level films also, where we have seen that by changing the focusing condition, you can increase the blow of shock velocities. But what we observed is that in micron thick films, we have observed these cone-like flare structures, where nanometer films will give you only the pure shock waves. And these are the samples after the ablation of the material. And this is the results we got from here, where we to show that by using F2 condition from the nanometer films, we can generate high blow of shock velocities with respect to energy. For lower energies, we will use F2 condition, and for higher energies, we can go for F1 conditions. And this study is also extended to the polymers. It's composite polymers, where we will use gold nanoparticles added to PVA fiber, and we have done the shortography analysis of that. It shows that the results shows that the PVA and IUPVA is giving higher velocities compared to the general aluminum and copper at 50 mil energies. So we optimized the energy for 50 millijoule, and we studied the process here. So these are the highlights of our work, and this resulted in a publication in JPSD. And coming to the third chapter, it's a dynamic spatial confinement air plasma and shock waves in millimeter cube, where we will apply obstruction along the radial direction. So this can, most of the study reports are available on this one, but they didn't visualize the technique, how it will evolve inside the tube. So we have tried to visualize the confinement by using this. If you see that a cylindrical glass tube, if you take, we can't see what goes in, what happening inside the tube. So what we have done is that we have done a rectangular glass tube where we can see internal dynamics of the plasma evolution and the reflection of the shock wave, and then compression of the plasma, which will generate to the secondary shock wave also, which is important in this confinement. So if you see the dynamics, shock wave dynamics, where here you can see that the shock wave generated, okay, shock wave generated here reflected from the surface, and will again travel into the core, and it will pass through each other, where we have observed that the plasma length is increased at the execution of this cone-like structure, we call as but they haven't resulted in the shock wave velocity increment. So the same thing is applied for cylindrical SS tube, where we have seen that there is a improvement in the axial shock waves, because the tube diameter is equivalent to the size of the plasma dimension, so that you can generate, you have the effect on the thing. These are the highlights. And coming to my last chapter, where we can see that LSP, where when you incident laser on the BK7 glass, you can see that there is a simultaneous generation of ablative and the shock wave and the recoiling shock wave inside the material. And in this thing, you can see that as the energy increases, the streaks optical breakdown in the material also increases, and there is a self-focusing effect happening here, which is raised to very sharp streaks here. And because we have calculated the self-focusing thing, which is 0.8 megawatts as a critical power, but we are using from 0.5 to 2 joules, which is more than that. And these are the shock velocities inside the BK7. And we are attached to a copper and aluminum sample in the confined ablation, where it won't distract the BK7 glass, and we have observed the shock waves inside the BK7. And the same study is observed in the confinement. We can say that pressure is directly proportional to acoustic impedance and the intensity. And the effect of acoustic impedance and intensity also studied here by using different geometries. And if you see the effect of acoustic impedance, we got the higher results for copper, confined with copper, than the aluminum. But when you change the focal plane shifting, the results for aluminum is shown higher in the F2 condition, where we shifted the focal point to 6 mm inside the target. And these are the highlights of my talk. And the thesis, I will do that. We have done the different confining methods which lead to the efficient plasma and shockwave generation. Then we studied the shockwave interaction to understand how the fluid confinement works, which led to the plasma jet formation. And we have proposed a method for efficient coupling of laser energy to the material in the confinement by modifying the laser focusing condition. And fourth chapter, we will learn spatial confinement plasma and the dependence of the plasma and radial shock waves with respect to the tube aspect ratio is clearly understood. And we have studied two applications, and key role of relative acoustic impedance in the confined LSP process is understood. And we have optimized the laser and focusing condition for efficient plasma and shock waves, which is used for the laser-based millimeter shock tube. And these are the recognition of my work. And this is my group. Thank you.
Yeah, thank you, Dr. Nagaraju, for facing at proper time. Dr. Sina, can you?
Yeah, good morning, Nagaraju. I have two simple questions, okay? The first one is,
Yes.
why did you use 532 nanometer as your probe beam? Was there a reason, or you could use any wavelength?
Yes, we can use any wavelength. I have used 632 nanometer Heaney as a probe.
Okay, okay, 632.
Yeah, 632.
You can use any wavelength? You think can answer me.
It depends on your detector. My SCD responsive is higher for the 500 to 700 region. So I have used the 632 as my probe.
So it's only the detector which determines which wavelength you use as a probe. Sure.
Yes, and another thing is that the transmission through the plasma also. I mean,
okay, let me go to the second question. Second question is that you say your work helps in laser shock peening. Have you correlated your shock wave to the quality of laser peening or something of that sort? How does it? How do these two connect?
Yeah, actually, if you do the shock peening, you don't know what happens inside the material. So what we have done is by using different confining layers, we observe the shock wave inside the material in BK7, so that we have an idea of which sacrificial layer we have to choose, what is the spot size we have to go. Still, it is optimizing. We are doing that process by using different spot size focal geometries and different confinement layers. And we are doing the characterization of these materials.
Dr.
But there will be no laser peening in case of glass, no? BK7.
No. Just to visualize inside the dynamics only, we have taken the BK7.
So at some point, you have to correlate the two. The shock wave, how it is propagating or whatever, and the quality of laser peening.
Yes, ma'am. We have to quantify that. Actually, we are in the process. But one more thing here is that the dimensions of the material itself acts as a confinement, which will give rise to the reflections in the shock wave, which will disturb the residual stresses and
Professor Ghosh,
to the tensile stresses.
Okay.
Okay, yeah, so I just have a quick question. So you just mentioned about self-focusing. So can you explain what is that and how is it playing a role here?
Self-focusing is because of the interplay between the Kerlins effect and the plasma defocusing. There is a formation of the channel kind of thing.
Question is more basic. Self-focusing, is it a linear effect or a non-linear effect?
No, sir. It's a nonlinear effect, which depends on the nonlinear refractive index, which is n equal to n0 plus delta ni. By changing the intensity of the laser, you will get the nonlinear effects inside the refractive index.
But we know different kind of nonlinear effects require certain symmetries.
Yes.
So in this case, is any symmetry of the system is needed or not? Do you understand that? Like, for example, second harmonic generation, you need some non-centrosymmetric system. Okay.
Yes, sir.
So it's a nonlinear effect. But here, what we are talking about is that the modulation of the refractive index by intensity. So are certain symmetries required for this nonlinear effect to take place?
Yes. I mean, I won't comment.
Okay. Okay, I'm done.
Dr. Bharma? RRCAT, Dr. Bharma?
Yeah, I have just a quick question.
Yes.
You have used shadowgraphy, right?
Yes, sir. Yes, sir.
Why not any other optical techniques for visualization, for example, Schlieren or interferometry, and how does it compare if you use that? Because you know, shadowgraphy is difficult to extract the numbers out of shadowgraphy. But if you use maybe interferometry or Schlieren, it is one order or two order of computationals are less.
Yeah, of course, sir. But thing is that the shadowgraphy is easy to align than the interferometry, because in interferometry you have to get the phases. You have you have to get the phase out of the interferograms, and you have to analyze. But shadowgraphy will give you the direct evolution, so that you will have a temporal and a spatial.
No, that is precisely the question. The question is, in shadowgraphy, the intensity profiles are related to the double differentials of the pressure or the refractive index field. So to extract the refractive index or any, for that matter, any experimental parameter for shadowgrams, you require two different integrals, right? So you have to integrate twice your intensity fields, and that will lead to your computational errors. But in case of interferometry, the phase is directly related to the intensity.
Yes, sir.
Right. So yes, I mean, it is easy to align, but it is extremely difficult, and to get error-free numbers, parameters is very difficult in shadowgraphy, but still you use it. So can you just justify?
Here we are, we use for visualization of the technique. We haven't captured the exact refraction.
Okay, so you have just visualized the, and you have not used that for quantification.
Quantification, yes.
Fine. So I think that was the only question. Thank you.
Professor Tata. Professor Tata,
you are muted. Professor Tata is muted.
Professor Tata, okay. I think.
No question from me.
Okay, fine.
Yeah.
I think move to the next one.
Our next presenter, Della Thomas.
Sir, I'm there.
Please start. You are audible. Please start.
Okay. Sir, shall I start?
Yeah, please.
Okay. Good morning, everybody. My name is Della Thomas, and I'm presenting my research work on the topic Influence of Biofouling on Sheet Resistance and Laser Spectroscopic Analysis. I work under the guidance of Professor S. Surendran, Department of Ocean Engineering, and Professor Nilesh J. Vasa, Department of Engineering Design, IIT Madras. So just a minute, some problem.
You are losing your time, please.
Oh yeah. Marine biofouling is the undesirable accumulation of biological organisms on immersed surfaces. It could be a static or a dynamic surface like a ship hull or rocks, and it affects all areas of the ship. So marine biofouling is actually a very complex community, and we can see that various organisms attach over a period of time, conditioning film to microfouling to macrofouling. And over a period of few months, we can see that the thickness varies from about 100 nanometer to about 1 centimeter. So in order to find a solution for the problem of biofouling, we have to actually understand the process. The main processes in its formation are settlement, proliferation, detachment, and predation. So in the final stages of biofouling, this much thick barnacles are also formed on ships. So it's an issue of grave concern, as a lot of fuel consumption and economy, a lot of crores of money are involved in this. But the existing methods are not a complete solution to the problem of biofouling. Presently, the coatings available are anti-fouling paints, which are copper or tin based, which are of concern to environment, and fouling release paints. But still, they have not been able to wipe out the problem of biofouling completely. And in order to measure the level of biofouling, the techniques are onboard sampling and laboratory testing, where we examine the SEM images. The objectives of the study of the thesis were to simulate the influence of fouling on the resistance of ship hulls and determine the effect experimentally, to extend the simulation to voyage simulation for specific routes considering weather conditions, to demonstrate an application of laser-induced breakdown spectroscopy to study the elemental composition of biofilms in laboratory-controlled condition, to extend the study to biofilm growth on different materials. So towing tank experiments were done at IIT Madras with various roughness. In order to do simulations, we have employed MaxSurf, ShipFlow, and also WAM and wave buoy data were taken. Laser-induced breakdown spectroscopy, analysis of biofouling, actual biofouling samples were also done, and a principal component analysis technique was done on the spectra. So this is the flow chart which was employed, methodology. There are two parts for this work: ship resistance studies and LIPS analysis. So simulations, experimental studies were done, and voyage simulations were also done. In LIPS analysis, the elemental composition were determined for marine biofouling on different substrates. Constituents were also analyzed. Growth and spatial LIPS analysis was also done. So this is the flow chart for both the work, ship resistance studies and LIPS studies. So in the case of ship resistance studies, as we already explained, simulations, roughness simulations using Danville's and Salvinson method, the environmental parameters were added, and we had established the surge equation, and voyage time and distance were calculated for different loading conditions. In the case of LIPS studies, we have actually determined what are the constituent species, and lip spectra were collected in order to determine the elemental composition. So now coming to the results. So this was the ship model which was used for simulations. You can see the various views here. And the main particulars of the actual ship, the model is of 1:100 ratios. So actual particulars can be also seen here. And fouling conditions, thickness conditions which were used for simulations are shown here. So we can see typical new coating, the thickness comes to only about 150 micrometer. With fouling, the thickness increases to about 10,000 micrometer. So it's a lot of thickness and a lot of resistance. So this is the experimental setup. The experiments were done at towing tank setup at IIT Madras, and this is the ship model we had made use of. And this is the connection to the towing tank. We had made use of load cell, 10 kg. Calibration plots are given here. And the simulated and experimental plots were found to coincide. So we could validate them. And we had also fabricated a setup in order to include the roughness. Here from about 2 mm to 4.75 mm, different biofouling conditions were included in this unit area setup. And the frictional plots are shown here. So by plotting all the results we have obtained, this is the plot we see for different fouling conditions. And a new algorithm was also proposed by which, with the help of calculations, we could determine the average velocity for various fouling conditions. So like the calculations were done, and here actually the average velocity attained for different fouling conditions have been calculated. So it was extended, simulations were extended to experimental, and simulation studies were extended to voyage route. We had considered the route from Chennai to Singapore, and the data buoy giving the wind and wave data was positioned along the route. And we have collected, we have simulated the data for about 6 months. And this is the surge equation which was used for calculation for estimating the voyage time and distance. So here we can see the results. The wind were included in the simulations. The wave, added resistance due to waves, and fouling. Wind, wave, and fouling were included. And we have calculated the time and distance required to complete the voyage from Chennai to Singapore for different loading conditions. So we can see that this approach is a pointer towards additional fuel requirement for vessel facing rough weather or overload conditions. Due to heavy calcareous fouling, about 41.67 increase in resistance could be observed. And coming to the next part, that is the LIP studies, the biofouling samples were grown on stainless steel substrate and FRP substrate. So as you can see here, the growth period varied from about 5 to 20 days. We can even see the barnacles here. And here the same images show the constituent bacteria and algae species, some of the bacteria and algae species. We have also done contact angle measurements, which show that stainless steel substrate is more hydrophilic, which explains its increased growth, increased biofouling growth, as you can see here in comparison to FRP. So laser-induced breakdown spectroscopy setup is shown here. So LIPS technique was employed, whereby the laser was focused with the help of lens onto the sample. The sample can be in any state. The actual biofouling sample was kept, and the emission spectra were collected with the help of lens and coupled to spectrometer. So since the plasma has lot of species, ions, atoms, and molecules, we have also adjusted the detector gate pulse with the help of delay generator. So all the parameters are shown here. And for ablating the biofouling samples, the laser pulse energy of about 42 millijoule was required. So LIPS is a very advantageous technique, as we can no sample preparation is required and real-time analysis can be done. So now we had also selected a few constituent species. These are lab grown, and we had selected a few bacteria and algae species. Bacteria species selected are Bacillus subtilis, E. coli, and Pseudomonas aeruginosa. These were cultured, and the sample preparation was done in the Department of Chemistry and Department of Biotechnology, IIT Madras, and the element LIPS spectra were determined. And the algae species which we had used were Ketochlorenscianus and Nischia sigma, as you can see here, which were obtained from NIUT Chennai. And these are the biofouling spectra obtained on FRP and SS. And here we have tabulated all the results. The major elements observed were sodium, potassium, magnesium, calcium, and trace elements aluminum, iron, zinc, boron, strontium, silicon, barium, etc. were also seen in the samples. CHNSO data was also taken. So here we have actually classified and clustered with the help of PCA technique. The entire spectra can be converted to a single point with the help of PCA technique. So it's a very simple technique in order to identify which are the constituent species which are present in a given sample. So, and we can see that with the growth, the clustering was found to spread out. So it's a very simple technique in order to identify the constituent species. Pellet samples were also, lead spectra was taken, and it was found to give a better spectra with lower noise. So it was possible to establish the LIPS technique in in situ conditions for acquiring the spectra and its rapid classification using PCA technique. So these are our visible research output. I wish to thank my DC members and also for the samples, Dr. Merilima Tilagam, NIUT, and professors from IIT Madras. And I wish to thank SAIF IIT Madras for helping with analysis and my lab mates and friends. Thank you.
Thank you, Dr. Dela, for the nice work. Just quick question, that what is your repetition rate of your laser? You are using the fundamental of NDAG. You did not mention that. Is it are you optimizing the repetition rate or is it a single hertz?
No, sir, it's a single, single.
So,
single pulse.
Yeah, but another thing, you have no calibration curve. I don't see concentration. You are telling you have detected so many atoms of the bacteria. That can be done in the lab also. Of course.
Sir, can you please repeat concentration curve for?
Yeah, for calibration curve, because how you are able to measure that LIPS is giving you the spectra, but the concentration of the elements. you have to calibrate it with a sample composition similar matrix. Are you doing that?
Okay.
Or you're not doing
Okay.
calibration?
Sir, actually, we had, means this has two parts. So we have done with very few samples, with like one set of samples. So calibration, it has to be further done. Calibration plots and concentration, all those have to be actually done. It is being done extended. Yeah, we are doing this.
Okay.
Yeah.
Professor Tata?
Yeah. I just have, what is the message which you give with respect to biofouling just by doing elemental analysis?
Okay. Sir, our like this this is a pioneer work where laser-induced breakdown spectroscopy was used to check the elemental composition. So, sir, we
That
are
is
just
known.
yeah. So, sir, what we are just trying to do is that, sir, if we are able, it will be helpful in formulating new coatings. Like, sir, if you are able to repeat the
No, by knowing just elements, do you think you can develop a coating which is suitable for against biofouling? I thought you should know compounds, right? And its reaction with the substrate, which is your ship material.
sir,
So by just elements,
this is
will it help? That's what my question. Yeah.
so this is a preliminary work, but
Okay.
so what we can do, we have like ship resistance studies we have done. So on with the combination of both, sir, I mean the resistance data, I mean whatever we have simulated, as well as the so LIPS elemental data. So not only for this growth from 5 to 20 days, but it has to be we are still
Okay,
trying
my
to
second
repeat.
question. My second
Yeah,
question.
please.
Okay, my second question. Since you have algae as well as different type of bacteria, okay, do you think depending upon the substrate, probably if it is stainless steel here, which is the most species which leads to biofouling? Is that study has come out?
Okay. Sir,
Which is more leads to out of algae versus different species of bacteria?
okay. So more fouling is caused by bacteria. Algae usually grows towards the
In
end.
bacteria also there are various manganese oxide, ferrous, iron,
Yes.
many elements. So which is the bacteria which you do think is most damaging here or leads to more fouling?
Okay. Sir, it is a very complex community, biofouling. So most studies
Thank you,
have to
thank
be
you,
done.
thank
We
you,
have
thank you.
selected a
Yeah.
few.
Yeah.
Thank you, sir.
Professor Ghosh, you want to ask any question?
Yeah, so my question is regarding first question is on the principal component analysis. So what does the principal component signify here in your case? You showed that graph that PC1, PC2, etc. So can you tell me that what PC1 means here in terms of its spectra?
Sir, here PC1 and PC2.
So why not hire any other PCs you are taking?
Sir, voice is not clear. Sir, you are asking about PC, right, sir? Principal components.
So that's what I'm saying, that let's say you have a spectra, you have many series of spectra, and you find out principal components. Why are you taking only two principal components, PC1 and PC2? And if so, what do they signify, PC1 and PC2?
Okay, sir, here since the spec, sir, we just took a 2D PC1 and PC2. We just took a 2D just to sir, since limited means limited spectra were only seen. We just wanted to see sir, on plotting the constituent as well as the biofouling spectra.
No, let us not go into the biofiling. Let us say I have 100 number of spectra. So when you do a principal component analysis, the idea is that to reduce the dimension, right? To reduce the number of data, and I want to represent them with some components, principal components. So that is what my question is, that you have a multi-component system, like so many elements, they have different signatures in the breakdown spectroscopy, breakdown spectra. So how do you decide that there is only two components that you are using for this
Okay, sir,
classification?
we did principal common analysis about 100 spectra we had taken, and sir, means the like with PC1, PC2, majority of the variation was getting we could means was getting terminated. So we just plotted
that is what one
PC1
needs
and
to know
Dr. Bharma?
statistically what was the variance.
Sorry.
Like if you take PC1, PC2, and then let's say if I include PC3, what are the differences in the variance level? So do you have an idea?
Sir, we had plotted. Yeah, we had plotted.
Just another. Okay, I understood. So another quick question. So why breakdown spectroscopy? Can you not use other spectroscopic techniques here, like let's say Raman spectroscopy? Can this be used also?
Sir, we had, yeah, sir, I mean, you are right, sir. Because of lesser time, we had just done with breakdown spectroscopy. All the other techniques have been actually studied by various groups. Biofolding is a huge research area since a lot of money is involved. So all the others have been already done.
Okay.
Laser-induced breakdown spectroscopy was this is a new work. It has not been done. First results, yeah.
But the Raman study you can do online also. LIPS has the advantage of online doing.
Yeah, sir. We can actually we can do it on actual fouling samples. Sir, we had actually.
Of course, other techniques are more sensitive at there.
Any spectroscopic technique, Raman, you can do online in situ. So that is why you use any spectroscopic technique. So the question is that why LIPS is so unique here?
Sir, all the other have been done, but LIPS data have not been done till now.
No,
so,
but is there any relative advantage? No, there must be some relative advantages of different techniques, right? So when you use LIPS, it might have some advantage. Use Raman spectroscopy might have some advantage. So that's what I wanted to know. Okay, I think
the advantage of LIPS is that like minimum sample preparation and in situ real-time analysis.
So that any spectroscopic technique
no
has,
need of
right?
any.
So that is what optical spectroscopy, any optical spectroscopy you use, so that is can be done in situ and minimum sample preparation. That is
but LIPS, you can do on actual fouling samples. That is the major advantage.
So any optical spectroscopy technique, you can shine light and you can
you can do sampling and you can do it. Dr. Bharma, any quick question?
Yeah, just a quick question. You have done two different studies. One is on influence of biofoiling on ship resistance, and then of course the LIPS studies.
Yes, sir.
Can you just correlate and how one is feeding to your other studies?
Sir, sir, in the like I worked under two guides, so we had worked separately on both ship resistance and LIPS analysis. But the correlation towards both in the development of new fouling coatings is that the elemental composition results and the ship resistance studies, whatever we have done simulations, it can be combined for for formulating new coatings. Means the labs do both the resistance studies as well as
but you have not reported that. You have not done that type of correlation. So these two seem to be very disjointed studies in your thesis.
So right now we have not reached that stage, but we are continuing the experiments.
But you have submitted the thesis, no?
Yeah, that is true.
So for this thesis, we could only do this much.
Okay.
Yeah.
And when you're showing LIPS result, we were expecting that you would show us the concentrations also of different elemental species which you have been able to determine, but that is missing. And I think that point was also made by Dr. Ray.
Sir, yeah, I mean, samples were very few, sir, and we are still continuing calibration.
Okay, I think
please.
Fine.
Can you move to the next speaker?
So our next presenter is Mr. Janpat Elayya. Mr. Janpat, please start.
Hello, sir. Am I audible, sir?
Audible. Mr. Janpat, please start sharing your slides.
Sir, Dilla Thomas will stop sharing.
Sir, how to do?
You can start sharing, Mr. Janpat.
Please start.
Good morning, one and all. I am L.A. Janapati, a research scholar from University of Hyderabad, I'm working with Dr. P. Premkiran. Today I will talk about the laser-induced underwater acoustic signals and the applications. So I will outline of the presentation is in this is divided into 6 chapters. One is first one is origin of the laser-induced underwater acoustic signals. It is called as LIAS. And the second one is experimental details and specifications. LIAS, and third one is LIAS in generation and the interaction across the water interface. And fourth one is feasibility study of laser-induced sonar. And fifth one is acoustic signals from nanosecond laser-induced underwater filament, summary and conclusions. List of publications, conferences I have presented in various conferences, academic references. So objective one is origin of laser-induced underwater acoustic signals. When high-intensity laser pulses interact with the water medium, various phenomena occurred. Those are absorption, catastrophic ionization, and at the end of this, it leads to laser-induced plasma formation. The plasma itself a source of optical emissions, cavitation bubble generation, shock emissions, and acoustic signals. So this is the typical experimental setup in our laboratory. This is the side view of the water chamber. This is the top view of the water chamber. The laser is focusing this direction. Here the plasma underwater laser-induced plasma formation in this. And the various positions hydrophones was immersed in the water medium. These are the hydrophones, response of the all hydrophones available in our laboratory. Those are the Teledyne Rezone hydrophones and needle hydrophones. And I have used the two laser systems. One is nanosecond, picosecond, another one is picosecond. Only 532 nanometer only. This is the experimental schematic for the generation of LIAS and their interaction with the water interface. So in 90s, laser pulses focus to the 150 mm focal length into the water chamber, and it generates the laser-induced plasma formation. The plasma itself is a source of acoustic signals, and the generation of acoustic signals propagates across the medium, and the hydrophones was received the signals. And here this one is microphone and kept at a distance of 4 centimeters away from the water interface, and the hydrophone immersed in the water medium only. This is the typical response of hydrophone in water medium for 25 millijoule energy. And in this study, mainly I have studied only one-dimensional signal to two-dimensional image, two-dimensional. This one is the temporal, only time signal. And this one is the STFT signal, STFT plot, and it gives the visualize the STFT visualize the arrival time and spectral content of the layers. So this is for 25 millijoule. With increasing laser energy, the peak-to-peak frequency pressures are increasing. And reflector signal, this is the direct signal, and this one is the reflector signal. This one is the reflector signal from water interface. As increasing the energy, the peak-to-peak pressures are increasing for both direct and reflector signals. This one is picosecond laser and picosecond pulses. But here the peak-to-peak pressures are maximum 30 kilopascal. Here it is 150, 5 times higher than for nanosecond lib. It persists the longer distances for underwater acoustics. So STFT means it simply compute it divides the window, divides the segments of the signals, and each window computes the FFT. It gives the arrival time and frequency content of the signal. So LIAS interaction across the water interface. Some of the energy is transmitted across the water interface that I have observed. And this is the simulation by using COMSOL multiphysics software. So recently I have started working on this. I have observed this one. some of the energy is transmitted across. So the water interface is no longer be a perfect reflector. These are the corresponding frequency spectrum. So this is the coming to the objective for feasibility study of laser-induced sonar. So I have used the I have immersed the various samples like sand-filled plastic and sand-filled glass glass underwater targets immersed in the water medium. Here I can show you clearly. So this is the water interface, and also some partially immerse the plate type targets. These are the solid type targets. So along the laser direction, perpendicular the laser direction. You can clearly it shows the at what distance it is. So these are the results for plate type targets. So this is the time domain signal. This is the time frequency domain signals at various samples. For incident and input laser energy of 30 millijoule laser energy only. These are the extended zoom view of the laser induced the reflector signals. This is the critical view of the schematic for generation for the propagation across the interface. When laser induced underwater echo signals strikes the objects, how it reflected. Here I kept it various distances like sand-filled water and sand-filled plastic bottle and glass targets also I have used. These are the response for plastic, sand-filled plastic and sand-filled glass targets. This is the water interface signal. So upon reflection, the higher frequency components are disappeared, or the lower frequencies are appeared for plastic, and glass is little different than the plastic, and water interface is also different than this one. So based on this, I can classify where the object is location and what are the objects. These are the feasibility study. It gives the feasibility study of laser-induced sonar. Coming to the experimental schematic for the nanosecond laser-induced filamentation in water. In this experiment, I have used, I have verified with 80 mm lens to 600 mm lens, but I didn't get any filamentation. But when I used the 1000 mm lens, I have observed the filament formation. The hydrophone was kept at a distance of 1 centimeter away from the source, and here I can show. Here I have scanned the hydrophone along the laser propagation direction. The peak-to-peak pressures are at the middle of the filament, or peak-to pressures are higher than the edges, starting and ending. So I have obtained these pressures by using the hydrophones. Another one is I have used the Maya spectrometer to collect the stimulated Raman's forward stimulated Raman signal. This one is the only I have observed. I have received the only 649.8 Stokes signal, and I didn't see the anti-Stokes Raman. These are the filamentation images for as a function of laser energies, and this is the time frequency domains of the signal. Applications. So LIAS has various numerical applications, including laser surgery, micromachining, remote acoustic source generation, laser generated high voltage water switches, and also stimulating blast wave. Apart from these, LIAS has both naval and commercial underwater acoustic applications. So underwater surveillance operations, port monitoring, object recognition, marine studies, etc. Summary of some of the thesis and conclusions. The evaluation of the LIAS and their characteristics from the nanosecond and picosecond laser pulses compared. The LIAS we have concluded those nanosecond LIBs pressures, peak-to-peak pressures and their frequencies are better than the picosecond laser pulses. It is suitable for nanosecond lib is more suitable for the remote acoustic source generation. The layers interaction across the water air interface and water air solid interfaces have been discussed in this thesis. The peak to peak overpressure of nanosecond lib is four times higher than the picosecond lib. So the layers of nanosecond lib is more suitable for remote detection and location of underwater objects via acoustic mapping. The layers is more suitable, useful for underwater acoustic applications, including communications, target recognition, navigation, imaging, etc. As it spans over the frequency range of 10 to 800 kilohertz range, over the frequency range of it spans over the frequency range of the underwater, and over the frequency range of 20 Hz to 140 kilohertz in air medium, useful for the proof of concept of acoustic signals where laser pulses, acoustic signals produced by airborne lasers. So the STFT spectrogram is visualized at the arrival time and instantaneous frequencies of the layers simultaneity. The characteristics of acoustic emissions emanated from nanosecond laser-induced filamentation of water have been studied in temporal and time frequency domains as a function of laser energy. So eventually, this kind of source is more suitable for feasibility study of laser-induced sonar.
Yeah, thank you for presentation within time. Okay.
These are the list of publications I have
I
have submitted.
Yeah, we know that you have
got
submitted
the best poster award in ICOL in 2019.
Thank you. The time presentation. Just a quick question. That you mentioned that you have a lower frequency, 105 kilohertz, that is transmitting peak frequency, that is transmitting to the water interface. But the higher frequency, like 690 kilohertz, that is not able to transmit. Why it is so? Is there any you have any total internal reflection takes place? Water air interface also?
So the higher components, higher frequency components are disappeared. It's around 690 kilohertz range. It may be the frequency, the water interface is no longer be a perfect reflector because some of the energy is transmitted across the interface.
Okay, and your work is, you have told many applications are there, but your work or data is focused to which application? For the laser, for the
feasibility study of laser-induced sonar, sir. Than the traditional sonar, it can be used the laser-based sonar.
Compared to other techniques like microwave techniques,
yes.
How it stands here for long distance object identifying?
Because electromagnetic waves can't propagate longer distance in water. Sound can propagate persist longer distances. That's why I used.
But you have a lot of hindrance will be there. A lot of objects will be there underwater. Let us say submarine. That's a very long distance, of course. There will be a lot of underwater. A lot of objects will be there which will be affecting that. Okay, but you have not done long distance. You have not done that. Very small distance you have tried. Okay,
in this laboratory study I have done, sir.
Yeah, I understand that. It's okay. Dr. Sujorita Sinha, you are there? Okay, if not there, Dr. Ghosh, Professor Ghosh.
Yes, I just a small question. So you did some COMSOL simulation of layers. So what did you do exactly? Can you elaborate what equation you solved?
Okay.
So in this, I have used the pressure acoustics module, pressure acoustic time explicit. As an input here, it is the point source generating the signal, simulating the signal. The input signal is this one is 30 millijoule laser-induced acoustic signal. Has given the input signal and proper geometry and proper mesh. Then it gives the.
Do you know that for this particular modeling, what equation does COMSOL solve here for this model?
So recently, I understood, sir. Recently, I have started, sir, 1 week back, 1 week ago. So mostly these equations are I'm not aware of that, sir. I will go through it, sir.
No, but actually, otherwise, the COMSOL can produce a lot of spurious results if you do not understand what equation you are solving, what are the boundary conditions you are using. Right? Blindly using COMSOL is not advisable.
No. Equation right now I can't tell you, sir. Those are the partial differential equations only.
That is true. Like for example, if you are solving light propagation, you will know that we solve Helmholtz equation. right?
Yes,
When
sir.
we are doing light propagation, so it's using COMSOL, you using Helmholtz equation. So what is that differential equation you are solving here? That you need to know. No, otherwise, what is the meaning of solving it?
Okay,
Okay,
sir.
so the other question is that you mentioned about some stimulated round scattering studies. What is that and why is that done?
So for nanosecond laser, it's very difficult to generate the filament. So because we need more energy, critical power is required to generate the filament greater than 1 megawatt to generate the filament. But with the by using these 532 nanometer, it is easily available. Readily available lasers are gives the that kind of peak powers. So here is I have observed only Stokes signal only. I didn't see the other anti-Stokes signal only.
Now, what was the purpose of this study?
This is the proof of whether the filament should form or not. The question is, that's why this is a supportive work, sir. For this one, scan along the laser action direction, because for all the focal geometry, it gives the point source, but here it is not a point source. It's like a channel. It's around 10 centimeter, 1 or 2. See here 1 or 2, 114 centimeter.
So why didn't you see the anti-Stokes?
So that is my seniors already have done this work, sir. But I don't know, sir. What is the
So you know, right? What is Stokes and anti-Stokes here? That you know, right? I know, I guess.
Just for supporting of my acoustic signals, sir. Whether whether filamentation is form or not.
I understand. I understand. But if you are putting something, you need to know the basis of that, right? That why you are doing it, and what is the fine that you are supporting it. But you have to know that what you are supporting with. Okay.
Yeah. Dr. Sucharita Sinha, if you're there. Dr. Sinha.
Yes. I think I have no questions.
Okay. Dr. Bharma, please.
Just a quick question. How do you decide the position of hydrophone in your experiments which you have done in lab? Because that is going to decide the signal which you're getting and the time periods and all those things. So these are all similarity experiments because you have to correlate with the real experiments, which are very in a very real dynamic field.
Before starting this experiment, I have positioned, I have immersed hydrophones at various distances, and it is closer to the source and away from the source. Where the reflection is coming from? Is it coming from water interface, or it is coming from the water acrylic water chamber? So I have verified that. Then I concluded to
those types of validation studies you should also include, because that will tell everybody that the position of the hydrophone has been optimized. I mean, in the chamber. Otherwise, you can place anywhere. I mean, you will get some signal, but that may not be the right signal to analyze. Right? And I again the question which Dr. Ghosh asked. I mean, this laser-induced filamentation. What exactly you are extracting from those studies, which you think will help you in these LUA studies?
So remote acoustic source generation, because femtosecond lasers can generate the filaments or the remotely generate the acoustic source. Is it possible to generate with nanosecond laser? That's why my purpose is, yes, nanosecond laser also can generate the underwater acoustic signals by using from filamentation.
Is it not known previously?
Yeah, it's known, sir. Only one person has presented the data.
So you know it that already that nanosecond lasers can produce laser-induced filamentations.
Yes, but acoustic signal nobody reported. That's what I reported, sir.
And what is the frequency of your acoustic signals?
So it's around for direct signal it has around 150 kilohertz and 690 kilohertz. When it interacts with the water interface and water solid interfaces, the frequencies are varying, sir. The spectral content is varying, and the
does it have any effect on your analysis?
Yes, sir.
What is that?
So here it is around 150 kilohertz, sir, and it one is around 390 kilohertz for plastic, and here it is the lower frequency components are disappeared for this glass when it interacts with the acoustic signal with the glass water field.
And
It's
where
around
do you
60
think
degrees.
these results will directly feed some field? What is the closest field you think these results can be utilized? You have shown so many applications where these LIAS
Yeah,
can
the
be used.
underwater mine detection, it can, so the LIAS could give LIAS like a laser based sonar, sir.
No, that is fine.
Where
In
the
your
object
introduction
is, you can
itself, you
see.
have written that mine detection and then submarine detection, all those things can be done. But what is the closest? Because I don't see that you have devoted any slide to that part. That these are the results, and I see my results getting utilized in this particular field in near future.
So this is a feasibility study of laser induced sonars only,
Okay.
because laboratory level we can go up to 40 centimeter distance, because laboratory dimensions, if I go to the 1 kilometer.
Of course, these are all similarity modeling studies, but then you do those scaling up, scaling down things in lab.
Yes.
And then you have to sort of extend those studies and scale up and then analyze your data accordingly.
Yes.
Fine, so I am done.
Tata, you have any question?
Just only one question. You simulated in the lab for a
Yes.
still objects as well as a still wave. That means the water is not moving. But
Yes,
in
sir.
actual situations, water is not still. Either it could be flowing or it could be wavy.
Yes, sir.
Similarly, your objects which you want to detect them are also could be moving. So what is the result? Your results will get affected by that motion. How do you treat them?
So the acoustic signal is omnidirectional, propagates across the media as a omnidirectional. So it can detect the whether a moving object or it's not a big deal to interact with
No,
this.
your spectrum will change or it will not change.
Definitely will change, sir. Definitely will change.
It will change in what way? Yes, it will change. Now what way? Okay. Think about it. Thank you. Yeah.
Yeah, I have the last question. Just as you told that filamentation, will help long filamentation? Will it help to generate more acoustic signal in the water?
Sir, I'm not audible, sir.
Hello?
Can you please read?
Hello?
Sir, yeah, audible.
Yeah, I think earlier referee also asked actually that longer filamentation length, will it help to generate more acoustic signal?
Yes, sir. Remotely, we can generate the source at what distance by changing the characteristics of laser pulses. Laser pulses.
Signal strength or peak to peak, your intensity to generate, whether your longer filamentation by the laser, will it help to generate more acoustic signal, or how you?
Yeah, it helps you a lot, sir. It helps you a lot because.
But in that case, picosecond laser would have been better for your longer filamentation.
Yeah, that's what I said.
Your study is saying
can generate filaments femtosecond, but the acoustic pressures are very low.
That you told the nanosecond laser is better for this study compared to, intensity is okay. Okay, fine. Thank you.
Sir, thank you, sir.
So now next speaker, Ms. Priyanka Baraskar. Ms. Priyanka, please start.
Yes, sir. I am sharing.
Hello, please start, please.
Yes, sir.
Don't delay. Use your time.
Screen is visible.
Yeah,
No.
visible.
Okay.
You share your slides.
Shared now. Now I can start.
No,
your
slides
slide
are
is not
visible
visible till now.
Okay.
Make it full screen. Make the slides full screen.
Sir, full screen. All right.
I think you are not sharing your PPT.
I think
You are sharing some other screen.
Yeah, you are not.
Stop
Hello.
sharing.
Okay,
Okay, sir. I am trying.
Your video is there, but
open the PPT and then share it.
So PPT is open. Screen. Entire screen.
Hello. Ma'am, in
Hello.
the sharing option, you will see that share your PPT. What you are doing is sharing your screen.
No, first click on the share button.
Share. I am clicking on share button. Choose
Then
what to share, entire screen or window.
So there will be options. So one will be your screen, other will be PPT. So wherever you see your PPT, just click there.
Okay, got it.
Yeah.
Is it visible, ma'am?
Yes.
Now make it
Yes.
Okay.
Can I start?
Make it full screen.
Sir,
F5. Just press F5.
Go to the
okay, so
presentation.
network.
Go to the presentation mode.
Network
There is
problem.
that
Just
presentation
press
mode.
F5 and go ahead. Start speaking.
Network problem. Can I start?
Yeah, please start. But
Okay, sir. Thank you so much.
expand
Good
your
morning,
screen
all
by
of you.
pressing F5.
Okay, sir. Good morning, all of you. First of all, I would like to thank and congratulate to organizer to organize such a wonderful event. Myself, Priyanka Bariskar. I am presenting my PhD thesis work, which has been completed under the supervision of Professor Pratima Sen at School of Physics, DAVV, Indore. The thesis comprises 9 chapters. We will discuss it one by one. Let's start with the chapter first, Introduction. The electronic and nonlinear optical properties is essential to design optoelectronic devices such as optical switches, memory elements, thin solid film, solar cells applications, magneto-optical switches, etc. The choice of the material which have chosen for making these devices is depend upon their response in the presence of applied electric, magnetic, and optical field. So for second, sixth, third, fifth semiconductor, organic compound, organometallic complexes were typically used for fabrication of these devices. The limitation of this material is that they can only respond in applied electric and optical field. Whereas transition metal oxide have added advantage over this material because they can also well respond to the applied magnetic field and become a, a center of attraction for making future multifunctional and high performance optoelectronic devices. In view of this, in the present thesis, we work on the chromium oxide and nickel oxide, which are appearing to be promising candidate material for various device application.
Priyanka,
And
your slide is not changing. We are on the first slide only we are seeing.
oh, sorry.
So you have to
network issue.
You have to expand it and then.
Okay, sir.
Or you have to click. F5 or full screen view, full screen. The bottommost that you press F5.
Sir, on my screen it is full screen on my system.
But here slides are
Press
not
press F5 on your computer.
Madam,
Press
you have shared the
F5
wrong
function
screen.
key.
You need to share the presentation on which it is full screen. Go back to the sharing mode again. See if you can see the full screen option.
Sorry, sir. Share.
Have you already started the FI presentation has begun? Or it is yet to begin? It will
Sir, I press F5.
Madam, do one thing. Just stop the presentation for a moment.
Okay, stop sharing.
So now just click on the share button.
Yes, sir.
Yeah, so now you will have options, right?
Screen and application.
Yeah. So in application, you can select the PowerPoint application.
Okay. Application.
And then there you will have option to select the PowerPoint.
Sorry, sir. Sir, in the application where...
You're not getting it? Then just share your screen. In the share option, you can just share your screen directly. Can you do that?
Yes, sir, I'm doing.
Yeah. Now just open your presentation there. Click on.
Now presentation is open. Is it visible?
Just select the presentation there on your screen. Open the presentation there.
Sir, presentation is open in my screen.
No, we are seeing your Explorer window right now.
Sir, is it visible, presentation?
We are still able to see your Explorer screen. In the share button, can you just select the screen thing? Entire screen?
Share screen, entire screen?
Yeah.
Yes, sir. I am selecting entire screen.
I think Priyanka, don't be nervous actually. I think you discuss with somebody and try to resolve. We'll come back to you, okay? Maybe we'll go to the next speaker, we'll come back to you. You'll get time, don't worry, please, okay? Please, you discuss with somebody, try to resolve that, but don't be nervous, we'll take care of you.
Okay, sir.
So Abhishek Chatterjee is there, can you just talk? You please.
So our next speaker, Mr. Abhishek Chatterjee.
Yes, sir.
Mr. Abhishek, are you there?
Yes.
Priyanka, you close your, you just.
Please share your screen.
Yeah. Visible, sir?
Not at.
Abhishek, start your presentation.
Yeah.
Are you there? Go ahead. Full screen and start your presentation.
Is it full screen now?
Not at. Press that. Okay.
Should I start now?
Yes.
So, good morning. Myself, Abhishek Chatterjee from RRCAT Indore. I have done my PhD from HBNI under the supervision of Dr. Tarun Sharma. The title of my thesis is Electronic Transpose Studies on Gallium Nitride epitaxial layer for the fabrication of radiation-hard ultraviolet photodetectors. As the thesis suggests, I have worked on gallium nitride wide bandgap semiconductor for the fabrication of radiation-hard photodetector. So before going in detail, let me introduce you with the gallium nitride in the context of semiconductor optoelectronics. I will discuss this briefly in two parts. First, I will discuss gallium nitride with light emitters and then followed by light detectors. Is the screen changing, sir?
No, not changing.
Yeah. Is it now okay, sir?
Yeah.
Okay.
Yeah.
It is changing now. Yeah.
So in light emitters, the major contribution of gallium nitride comes after the invent of nitride-based blue LEDs. Using highly efficient white light sources have become possible. This can be understood better from the following graph. For efficiency of white light, which is a measure of the perceived light power relative to the provided electrical power, is plotted. It is very clear with white light with an efficacy of 300 lumens per watt, a revolution in the solid state lighting by replacing the conventional white light sources of previous centuries. With this significant improvement, substantial energy saving is now possible. It is currently estimated that by 2030, approximately 40% of the power plant, 40% of the energy will be saved by using white LEDs, and at least 31 gigawatt power plants can be eliminated, can be stopped by 2030, and this will avoid generation of 185 million tons of CO2. So not only by energy consumption, white LEDs have considerable impact on the issues such as environment and even the health of the individual. There are several viable approaches of white LED. A first approach is converting a part of the blue light using white phosphor to yellow, and for human eye, the combination of blue and yellow light is perceived as white. The second approach is a multi-LED chip approach in which light emitted from 3 different LEDs of red, green, and blue combine and mix them to generate white light. Among the three primary colors, the red light emitters are invented in 1960s, and until recently, they are the only high luminance LEDs available for us. After many years of research, great advances were made in the direction of blue LED by growing high efficiency gallium nitride on sapphire, followed by demonstration of P-type conductivity in GaN by magnesium doping. These breakthroughs led to the first nitride-based high efficiency blue LED and green LEDs with efficiencies up to 10% in 1995 as shown in this figure. Rapid progress thereafter led to the first commercialization of the white LED which led to the current state-of-the-art white LEDs with an efficacy of 300 lumens per watt. The impact of this invention was so high that the three Japanese scientists, Akasaki, Amano, and Nakamura, were awarded the Nobel Prize in 2014. In the Nobel lecture, this invention is termed as the greatest benefit to the mankind, and the white LEDs are identified as the long-lasting and the more efficient alternate source for older light sources. Not only light emitters, but also for light detectors, nitride-based devices perform superiorly in UV detect spectral range. Due to the lower band gap, the well-established silicon technology has their limitation in the UV spectral region. On the other hand, being a wide band gap material, gallium nitride is intrinsically sensitive to the UV light. Also, wide band gap enables operation at high temperature and under high electric field. In comparison to silicon and gallium arsenide, gallium nitride has higher saturation velocity, which enables faster device response as shown in this figure. Not only this, but gallium nitride also having highest displacement energy, and this leads to their usefulness for the application under high radiation environment. Here are the several applications of nitride detectors. Some of them highlighted here in missile tracking, in high radiation environment, as in nuclear reactor.
Slides are not moving. I don't see slides moving.
No, for me it is moving.
Okay. Yeah, now, yes.
It is moving here.
Should I continue, sir?
Please continue.
For detection of oil spill in sea, also as personal UV monitor, and to track daily sun exposure in the form of wearable UV tracker are to name of the few. Having said that, we must not forget that every great invention have their own challenges. Same is true for gallium nitride also. One of the major challenges in gallium nitride is the heteroepitaxial growth, since no lattice match substrate is available. As a result of this, researchers were forced to grow it on foreign substrate like sapphire, but sapphire having a 14% lattice mismatch with gallium nitride, which leads to a high density of interfacial defect in the GaN sapphire interface, and it is found that this dislocation density reduces as it increases from the interface to top layer. Other than this dislocation, an unintentional N-type doping is also observed in GaN due to oxygen and silicon, which act as carbon and magnesium act as acceptors in GaN. Presence of this large density of dislocation considerably hinder the performance of based light emitters as well as light detectors. They increase the probability of non-radiative recombination, reducing the efficiency of the LEDs. Large density of dislocation also increases the dark current of the detector, resulting in the reduction in the responsivity of the detector. So having said that, the motivation of the present work is to understand the physics of electron transport in gallium nitride epitaxial layer in the presence of large density of dislocation and point defect, to demonstration of high performance GaN UV detector fabricated on gallium nitride epi layer in presence of such dislocation and defect, and finally to test the usefulness of these devices for the application under harsh radiation environment. To understand the mechanism involved in the electron transport in gallium nitride, we have investigated the temperature-dependent carrier concentration of GaN epitaxial layers by two complementary techniques, namely Hall and CV. For Hall measurement, the sample is mounted in configuration 1, and for CV, it is mounted in configuration 2. To understand the effect of growth mechanism on the electron transport, we have compared gallium nitride epi layer of same carrier concentration grown by two different growth techniques, namely metal organic vapor phase epitaxy or MVPE and the hydride vapor phase epitaxy or HVPE. Here we have found that two-order difference in carrier concentration measured by Hall and CV in case of HVPE grown sample as shown by the figure A. Moreover, the carrier concentration extracted from Hall shows a temperature independent flat region below 80K as shown by this inset figure of figure A. No such observation is made for MVP grown sample. From literature survey, we have found that the flat temperature dependence is an indication of the presence of a high density of dislocation at the GAN-SAFAR interface. So to further investigate it, we compare our data with that available in the literature, and the data is plotted in this figure. Here this yellow circle and the red triangles represent the Hall and the CV data. As can be seen in reference A1, the gallium nitride layer, the difference between Hall and CV data is 3 order, and this difference reduces to 1 order, increasing the thickness of the GAN layer to 13 micron. With further increase in the thickness for reference A2 to 20 micron, the difference reduces further. So this gives a clear indication that with the reduction in with the increase in the thickness of the GAN layer, the difference between Hall and CV will reduce. So this is actually some indication of some kind of this kind of thing. As you go on increasing your thickness of the GAN layer, your dislocation density is going on to reduce. So this is gives an indication. So we simulate the data, and finally we have showed that this Hall and CV data will exactly match only when the thickness of the GAN layer will be at least equal to 300 micron as shown by this inset red line. At CV and simulated Hall, both when we fit this data in this experimental, this fits quite well. So nowadays, the usage of gallium nitride template in epitaxial growth of nitride is often preferred. The importance is our result is therefore critical, where the dislocation might limit their transport in these devices. One might assume that the charge transport mainly occurring via this path to the bulk layer. However, in presence of such interfacial dislocation, most of the charge transport will governed by the interfacial path 1. Since this dislocation propagates up to the top gallium nitride surface, the next objective was to investigate their effect on the carrier transport across the metal semiconductor Schottky junction, which is fabricated at top of this gallium nitride epitaxial. So this is done in next slide. Here you can see that when the electrons are injected from the top, now they the contact is fabricated on the top of this junction. So we have here compared the current voltage IV characteristic of these practical devices with that of the ideal gallium nitride photo detector. While this ideal case we have considered only thermionic emission is the mechanism of carrier transport across this barrier. So as can be clearly seen, the magnitude of reverse current for practical diode is much larger than that predicted by the ideal diode considering thermionic emission model. Further, a highly conductive region representing by these black spots, which obtained from the scanning capacitance spectroscopy data, are also represented the dislocation region of, which act as a high conducting region. So this indicates that the ideal thermionic emission model is not suitable in this case. So probably thermionic field emission mediated by this tunneling across these dislocation regions are the dominant one. So here is the schematically we have shown this mechanism. So now since the barrier is thin because of the high doping, so carrier now can tunnel through this thin barrier rather than going on top of this barrier. So as a result, in practical devices, we have fitted this thermionic emission model in our data, and we've shown that using this blue line, it is shown that the thermionic field emission model is quite nicely fit with this practical case. So what is the repercussion is on device front? So when you make device on top of this sample like this, here also one will assume that the carrier transport is governed by path 2, but in presence of such dislocation channels, most of the carrier will follow this low resistance path through this interface. So it will hamper your device performance. Now the question is how to improve the device performance in presence of such high dislocation density in GAN. So we thought that surface passivation may be one of the possible beneficial for this regard. So we did this in our next slide. Here we have inserted a thin layer of oxide in between the metal and the semiconductor as is shown by this. And this is the real image of the device. And here we have compared the IV characteristic. We have tried two different oxide actually, SiO2 and ZrO2, and you can see that the leakage current reduced 8 times after insertion of this SiO2 and reduced 28 times after insertion of ZrO2. So this indicates that oxide passivation largely controls the dark current. And we also measured the spectral response of this device. This is the measurement setup, and here we have compared the responsivity of the 3 devices. And as you can see that the responsivity considerably spectral improves, as well as a flat region in the lower wavelength side also observed because of the surface passivation. So from here we concluded that both the oxide are better than without this having no oxides interlayered in between. But ZRO2 we have chosen because this is performed superiorly among the two oxide layers. So here we further investigate the importance of ZRO2 passivation layer thickness in the performance of the detector. Here we have measured the spectral and temporal response of our 4 detectors with having various ZRO2 thickness from 0 to 9 nanometer, and the responsivity and the temporal response of the 4 devices are compared here. As you can see that with an optimum ZRO2 layer thickness of 3 nanometer, the responsivity peaks and also the fastest response of the device is obtained. Another important figure of merit of the detector is the detectivity, which corresponds to the ability to detect weakest signal. So here it is worth to note that the detectivity of the photodetector that we have fabricated with optimized thickness of ZRO2 is found to be similar or better than the state-of-the-art values of the available detectors in this field when compared along with the dark current. So this indicates the improvement of the practical usage of our device as a UV detection purpose. So after improving the device performance, our final aim was to test the detector under high radiation environment. So here we have done that. Here we have used cobalt-60 gamma for this purpose. The displacement energy of gallium nitride is higher than that of gallium arsenide. Hence, it is expected that the radiation-induced damage in case of gallium nitride will be less than that in case of gallium arsenide. To illustrate this point further, we have plotted the change in leakage current after gamma irradiation in gallium nitride and gallium arsenide based Schottky junctions. As can be seen from the figure, there is a two-order change in the leakage current in case of gallium arsenide, whereas only a nominal rise in leakage current for gallium nitride. Further, the spectral response of pristine and 200 kilobay irradiated gallium nitride Schottky detectors are compared here. As you can see that after irradiation, within 16 hours of irradiation, 60% of the device response is recovered, and within a day the device recovers completely. So this signifies the compatibility of the device for operation under high radiation environment. We have also indigenously developed a nitride MVP system. The system is fully computer controlled. The photograph of the system along with the control panel is shown here. We have grown several nitride epitaxial layers using this system. A representative HRXRD and PL data is also shown here, where in HRXRD the 6 peaks confirm the growth of oxide gallium nitride structure, and the PL, the bandage and the defect related PL related to the gallium nitride. This indicates the growth of epitaxial gallium nitride. These are the few typical samples that we have grown in our system. More detail of this work is published in this journal. So in summary, we have shown that dislocation plays a critical role in the performance of gallium nitride based light and detectors. Presence of a large density of dislocation promotes the parallel conduction in GaN photodetector and deteriorated detector performance. A method to improve the detector performance is demonstrated by insertion of a thin layer of ZR2, which shows the state-of-the-art performance of the MOS detector. GaN photodetector are found to be beneficial and radiation hard as compared to gallium arsenide detector and can be recovered fully within a day after irradiation. Finally, density and location of dislocation in GaN template is a key factor for the development of gallium nitride-based devices. These are the list of journal publications, and these are the list of my conference publications. I would like to acknowledge Professor T.K. Sharma, K. Dixit, and Dr. Khamari for significant scientific discussions in my PhD work. All the members of SML, PhD, doctoral committee members, and HBNI RRCAT, HBNI Mumbai for their help and support during the work. Thanks to the organizers of NLS for giving me this platform to present my work. Thank you, sir.
Thank you, Abhishek, for nice work. Professor Tata.
Yeah, two quick questions. I want you to tell me if the recovery day thing is 1 day, how can I detect continuously the gamma?
No, you said this is the recovery after irradiation.
Yeah. So once you, let's say I have a gamma ray falling on the detector, and it creates certain charge carriers. But let's say I stop the gamma, it will take about a day to recover it. Then how do I do second experiment as a detector?
So the objective of this work is to not use our detector as a gamma detector. The objective is to demonstrate that in high gamma environment, this detector can be used. That means as a detector, you can use this in high gamma environment. So it will not damage. If you use silicon or if you use gallium arsenide, they will not work. In high radiation environment, they will damage. They will stop their performance. But our detector will stop in high environment also.
But it will damage anywhere second day.
So damage is very less. I have shown you that IV curve. Even 200 kilogray is not a small dose.
Okay.
We are talking about 200
I come back to the dislocation. I'm not understood why the dislocations are extremely important here. You project as though dislocations are important, not the material as such.
Just can I go to that figure so you will understand better?
Yeah.
Please go ahead.
Yeah.
If
quickly.
See, sir, you can even see from here in this top region.
This is your list of conference. List of conference publications. Now, okay.
Yeah. So now you are having this this is your template I am talking about at your dislocation. Okay. At the interface. Now you are making some
voice cut is there.
No, if I reframe my question, in case you change the substrate, because the dislocations are a consequence of misfit, okay? Because you are doing epitaxial. Suppose you have a lower density and a higher density. Can you demand? I think the demonstration of the role of the thing would be that, okay? But I don't see that type of thing here. Okay. It's doing the same experiment in another substrate, which will give you less dislocations.
Abhishek, are you there? His connection has some problem.
Yeah. Okay. Fine.
Abhishek? Dr. Bharma, can you just find?
Yeah.
Okay, he's there now.
Abhishek, are you there? Abhishek, can you hear us? Yeah. So, yeah. So
can you respond
to picking up from what Dr. Tata was saying? See, when we are growing any material or these dislocations, or for that matter, any defect has a role, and generally they have a detrimental role. Fine.
Yes.
And what it seems to be coming out from your work is that you have shown that the dislocations are somehow playing a very positive role in your epitaxial growth of gallium nitride sample. Now, can you first of all tell us what type of? Okay, let me just complete. Then you can come in. What type of dislocations you are talking, and how do you decide that the dislocation is of that type? See, it can be screw dislocation, it can be edge dislocation, it can be a mixed dislocation. And so, how have you imaged? Because I can see in your slide there is an image which you have shown from some other author, Chen et al. Materials today, right? So they have imaged some sort of dislocation map. So, how you have imaged it, and what type of dislocation are you talking of? I think your voice is not very clear. I mean, I can't hear.
Yeah, Abhishek is not getting disconnected. I don't know whether he's trying from.
You can.
Abhishek, maybe you can stop sharing and just answer the.
Yeah, you can stop sharing and you can just answer the questions.
Yeah, that may be better.
So some bandwidth would be at least released.
Telephone.
So stop sharing your video.
He's not listening, perhaps.
Hello?
Yeah. Abhishek.
Yeah, now you're audible.
Yes. So the question was.
Yeah.
Question was in general materials. What Dr. Tata was saying that. Yeah. Please tell. Please tell.
Yeah. Yeah. But I have
You're not audible, Abhishek. You're not audible.
Sir, just a minute, sir.
Shall we
Let
go
me
to
check
the
it.
next?
Yeah, now it is okay. Now it is okay.
Now it's okay. Yeah.
Please go ahead. You are audible.
Don't show. You just talk. Don't show any slides. No.
For mobile.
Abhishek.
Or shall we come back at the end after the other presentation, Dr. Verma? We can
maybe. Yeah.
Wait for a few minutes and.
Abhishek, are you there? We can come back to you in the end.
Priyanka also waiting.
1 or 2 minutes and we'll move to next.
You sort out the. Yeah, you are audible, but.
Can you respond? Abhishek, I think it is going on. And
I think we can come back to him.
Yeah. Voice is breaking.
Next speaker.
Yeah, so Abhishek, you try to resolve your problem. We'll come back to you after the.
Yeah.
If time permits.
You sort out your net issue and then we'll come back to you. Don't worry.
Our next speaker, Miss Priyanka. Miss Priyanka, please start sharing your slides.
Yes, sir. So slide is visible.
Yeah.
You can expand the.
First check that whether it is
Yes. Good. Go
Fine,
ahead.
fine.
With the
Go ahead.
confidence, go ahead.
Is it visible? Can I start?
Yes. It is visible.
Yes, please go ahead.
Thank you so much, sir. Good morning, all of you. First of all, I would like to thank the organizer to organize. I would like to thank and congratulate the organizer to organize such a wonderful event. I am myself Priyanka Baraskar. I am presenting here my PhD thesis work, which has been completed under the supervision of Professor Pratima Sen at School of Physics, DAVV Indore. My thesis title is Electronic and Nonlinear Optical Properties of Undoped and Doped Chromium Oxide and Nickel Oxide Thin Films. The thesis comprises 9 chapters. We will discuss it one by one. Let's start with the introduction. So the slide is changing now.
Yeah.
Okay. Thank you, sir. The knowledge and understanding of the electronic and nonlinear optical properties is essential to design optoelectronic devices such as optical switches, memory elements, optical and magneto-optical switches, etc. The choice of the material which are chosen to make these devices is depend upon their responses in electric, optical, and magnetic field. So far, second, sixth, third, fifth semiconductor, organic compound, organometallic complexes were typically used for fabrications as type of devices. The limitation of this material is that they can only respond in the applied electric and optical field. Whereas transition metal oxides have added advantage over this material, this because they can also respond to the applied magnetic field and become a center of attraction for future multifunctional and high performance devices. In view of this, we have chosen chromium oxide and nickel oxide appear to be promising candidate material belongs to the transition metal oxide group. And there is till now there is a very few studies were reported on their optical nonlinearity, and their additional knowledge of optical nonlinearity will greatly enhance the device possibility in these materials and open up the new areas for next generation devices. So we have chosen the chromium oxide and nickel oxide, and we have studied the undoped and doped chromium oxide and nickel oxide thin film. The samples were prepared using pulse laser deposition technique. The target of the PLD is prepared by following these steps of solid state reaction route method. The grown thin film have been characterized by using these following techniques to analyze these particular properties at various institutes such as UGC DICSR Indore, RRCAT Indore, NLO Lab, School of Physics Indore. Let's start with our work. The nonlinear optical properties is important for fabrication of optoelectronic devices which can be monitored by electric and optical field. If we study this property in the presence of applied magnetic field, it gives us an additional knob of applied magnetic field to monitor the future optoelectronic devices. and we are the first who have reported nonlinear optical properties in the presence of applied magnetic field. This work was reported on 2% titanium doped Cr2O3, which was prepared by pulse laser deposition technique. XRD suggests the crystalline character and rhombohedral phase of Cr2O3. Particle size is calculated by Debye-Scherrer formula and found to be 16.9 nanometer. Morphological study suggests the ellipsoidal shaped grain for the titanium doped Cr2O3. To study the linear properties in the magnetic field, we make this experimental arrangement. We kept the sample at the magnetic field using electromagnet and illuminated it with a spectrograph with UV visible radiation and recorded the resulting spectrum with fiber coupled cable of spectrograph. To study the nonlinear optical properties in the applied magnetic field, we make some modification in the conventional Z-scan technique. As we know, in the conventional Z-scan technique, we move the sample across the focal region to vary the intensity. If we want to study this property in the presence of applied magnetic field, we can't vary the sample in the magnetic field. So to resolve this issue in the present setup, we have mounted the focusing lens on the translation state, and by moving the focusing lens, we can vary the intensity on the sample, which was fixed between the magnetic pole. So we can study these important properties in the applied magnetic field. These are the laser parameter we have used for the present work, and this is the results. In the UV visible in the UV visible spectroscopy, we can see the broad peak appearing near the 2 electron volt, and absorption gain significantly modified in the lower energy region and unchanged in the higher energy region. So our region of interest lie below the 2 electron volt. So we study the nonlinear optical properties at 1.95 electron volt using helium neon continuous wavelength laser, and this is the Z-scan results shown here. In the absence of magnetic field, we observe a peak valley behavior corresponding to self-defocusing effect and suggest the negative sign of optical nonlinearity. As we apply the magnetic field, the additional features can be witnessed both sides of the focus attributed to the higher order optical nonlinearity. Further increasing the magnetic field, we can see the valley position shifted toward the focus. At the maximum magnetic field, we can see the peak valley is convert, and we can see a clearly valley peak position corresponding to self-focusing effect and suggest the positive sign of optical nonlinearity. To see this, such features establish the occurrence of sign reversal of optical nonlinearity under the influence of magnetic field and suggest the utility of the film in the magneto-optoelectronic devices and magneto-optoelectronic device applications. To see the magnetic effect, we perform magnetic measurement, and we see in the undoped film ZFC and FC curve shows the broad maxima at around 73 Kelvin assigned to be superparamagnetic blocking temperature, whereas ZFC and FC curves coincide at room temperature. In the titanium dope, the ZFC and finite separation between the ZFC and FC curve shows the some amount of magnetic ordering present to the room temperature. To confirm this, we perform room temperature field dependence magnetism, and we can see the saturation magnetization and coercivity increase due to the titanium doping. To explore the reason, we explore the oxygen defect states, because oxygen vacancies are magnetically active defect states and can be carry some magnetic movement. So we explore the oxygen 1s core level spectra, and we can see the oxygen vacancies is increased due to titanium doping from 16% to 48%, corresponding to 531.6 peak. And we can say that the structure, optical and magnetic studies of this film suggest the utility of film in the magneto-optoelectronic devices. As we know, to implement any material for device application, the knowledge of their band alignment on their interface is essential. In the next chapter, we study the band offset measurement using X-ray photoelectron spectroscopy. We have prepared 3 samples, 2 is single layer and 1 is bilayer of these 2 materials. We kept the bilayer is very thin to probe the X-ray on the interface, because XPS is a surface sensitive technique with low penetration depth. These are the repulsion parameters. XRD suggests the crystalline character and rhombohedral phase corresponding to 006 plane of Cr2O3. We have calculated the particle size, which are given here. To calculate the energy band gap, we perform UV visible spectroscopy. From top plot, we have calculated the energy band gap, and from the valence band spectroscopy, and by extrapolating the leading edge of valence band spectra, we have calculated valence band maxima position. To calculate the band offset, we have also need the core level position, and we perform the X-ray photoelectron spectroscopy, and chromium 2p and titanium 2p core level suggest the +3 oxidation states. And from here we can calculate the core level position after carefully and precisely determining the valence band maximum position, core level position, and energy band gap. Using this Kraut method, we have calculated valence band offset, and using this equation, we have calculated the conduction band offset. With this values, we have draw the schematic of heterojunctions. We have which is shown here. The figure shows the type 2 band alignment, suggesting the higher barrier height for hole to transport across the junction as compared to the electrons. It is expected this experimental finding added up the understanding of fundamental properties of bilayer, which is required for designing, modeling, and analysis of optoelectronic and magneto-optoelectronic devices. In the next chapter, we have focused our attention to our second important work, which is optical path length compensations. As we know, high power lasers are critically used for laser machining, drilling, quantum optical based experiment, sensitivity interferomagnetic based experiment, such as gravity wave detection, where the high power laser causes thermal expansion and leads to phase alteration. In such cases, phase compensation is required to accuracy the result and warrant proper understanding of optical nonlinearity. To complete this objective, we work on this system, and they work on this system undoped and 5% aluminum doped nickel oxide and bilayer of this materials. The XRD suggests the cubic phase of nickel oxide. The lattice parameter and particle size is calculated and given here. To observe the optical nonlinearity, we perform close aperture Z-scan technique, and in the undoped nickel oxide, we observe peak valley behavior corresponding to negative sign of optical nonlinearity, suggesting self-defocusing effects. Due to aluminum doping, the feature is revert, and we observe the valley peak corresponding to positive sign of optical nonlinearity, suggesting the self-defocusing effect. The experimental data is fitted with this theoretical formulation of Sheikh Bahai et al., and we calculate the nonlinear refractive index coefficients. Then why the nonlinearity occurs, we have explored linear optical properties. In the linear optical property, we can see in the S1, which is undoped nickel oxide film, the sharp increased transmittance near the band edge suggests the direct band gap and high crystalline nature. Decreasing the transmittance at the higher wavelength suggests the some defects present in the S1 film, whereas S2 and S2 in the S2 and S3 film, the transmittance is continuously increasing with increasing the wavelength. To confirm this defect states, we've explored the oxygen 1s core level spectra, and we can see the oxygen peak corresponding to oxygen vacancies presence in the S1 film and absence in the S2 film. So we can see and say that the asymmetric behavior of oxygen 1s spectra in S1 film, which is corresponding to oxygen vacancies, the dynamic deformation is expected to consume open space arising from the oxygen vacancies in the S1 film, which give rise to negative sign of optical nonlinearity, whereas in the S2 film, increasing the bond length within the spot size with increasing the temperature give rise to photo expansion and causes the sample to behave like a convex lens and positive optical nonlinearity. So the reason of optical nonlinearity is thermal lensing effect. This opposite kind of thermal expansions gives idea us that a thermal lensing effect and optical path length compensation is bilayer of this material can be done. So we repeat the Z-scan experiment in the bilayer, and we can see the bilayer in the from this figure, the bilayer film in the bilayer film we successfully obtained the optical path length compensation and a thermal lensing effect, which suggests its utility in the elimination of thermally induced aberration in the experimental one with high power lasers. In the next chapter, we make some theoretical formulations. Our research group also performed several experiments and see the deviation from the standard Z-scan features. Because the Z-scan is very sensitive to the aperture size, it is difficult to achieve ideal condition S is equals to 0 and S is equals to 1, and one can observe the deviation from standard peak value. The reason for is aperture size, simultaneous presence of refraction and absorption, and higher order optical nonlinearity. To resolve this issue, we make some modification in the existing theory. In the existing theory, delta phi is the nonlinear phase shift, which has which has its origin in complex nonlinear optical susceptibility. In the present model, we Assume the nonlinear phase shift is complex in nature, a real part corresponding to nonlinear refraction and imaginary part corresponding to nonlinear absorption. We replace the nonlinear phase shift in the existing equation and we get the modified equation which is shown here. S is equals to 0. At S is equals to 0, we can observe only dispersive effect. At for S is equals to 1, we can observe only absorptive effect. And for the intermediate value of S, where S is the aperture size, we can see the simultaneous effect of nonlinear refraction and absorption. To examine the effect of aperture size, we make some numerical analysis. These are the theoretical graph where we can see that the S is ranging from 0 to 1. For the intermediate values of S, we can see the deviation from the standard peak value. We have tested our validity of theoretical formulation with experimental support, and we have fitted our theoretical we have fitted this experimental data with our proposed theoretical equation, and we found that the F3 is we can found that when we take into account the simultaneous presence of nonlinear refraction, absorption, and aperture size, we find the best fitting in the asymmetric Z-scan curves. We also fitted our
Priyanka, you have 2 more minutes. Please try to.
Okay, sir. I have tried to conclude.
2 more minutes, of course.
Okay, sir. The close aperture Z-scan technique also is fitted with our equation. These are the fitting parameter. Using the equation, we calculate nonlinear optical coefficient, and we have for this effect, we develop a generalized theoretical formulation. In the next chapter, we study the magnetic properties in the 5% aluminum doped nickel oxide thin films. The presence of aluminum conformed with XPS, XRD suggests the cubic phase, and the defect states is confirmed with X-ray photoelectron spectroscopy, and oxygen 1s core level spectra suggests the more defect states is S2 film. And then optical property in the S2 film, increasing the band gap and decreasing the transmittance. The reason is for the reduction in the lattice parameter. The magnetic property suggests magnetic properties suggest the room temperature ferromagnetism in the S2 film, where the weak ferromagnetism observed in the S1 film. In the case of S1 film, we does not have any hysteresis loop, and S2 film we have seen the Moog loop, and suggest its high value of coercivity and retentivity suggests the utility of film in the magnetic memory storage device applications. This is the conclusion. In this all these grown thin films, we have obtained this important result, which appears in this following publications. This is our future scope. In our future scope, we will work towards the conductivity of the material to monitor, can be monitored by appropriate doping and growth conditions. These are the list of publications. And I would like to acknowledge my supervisor, Professor Pratima Sen, and sincerely thank to late Professor Pranay Kumar Sen for their continuously supports, and the staff members and as school of head of the department and UGC DACSR for providing us the experimental facilities. Thank you so much.
Thank you, Priyanka. Dr. Sucharita Sinha, are you there? Dr. Sucharita Sinha.
Yes, Alok, I have one question for Priyanka. She talks
Yes, ma'am.
about thermal lensing seen when she did
Z-scan measurement.
Z-scan using a closed aperture, no?
Yes, ma'am.
So, suppose you were using a nanosecond laser and you were to do the same experiment, repeat it again. What
Yes,
would you
ma'am.
see?
Sir, ma'am, in the nanosecond laser, there is a possibility of electronic transition for the nonlinearity. We use continuous wavelength laser. So because of
Yes.
continuous wavelength laser, there is no option for electronic transition. So nonlinearity is occurs because of thermal expansion,
No.
thermal lensing effect.
I'll ask you that same question again. Would you see a thermal lensing if you were to use a nanosecond laser?
Ma'am, I think this is depend on the material property. In the material, if the electronic transition is possible, the nonlinearity is become because of electronic transition. Otherwise, thermal lensing effect is there always possible.
It's always there. Thermal lensing. What is the decay time of your thermal lens?
Decay time of thermal lens is a dephasing time between the transition.
Dephasing time? Thermal lensing? Suppose
Thermal.
I shine my helium neon laser and then
Yes.
I
Okay,
switch it
okay.
off.
I understand the question.
Mhm.
Ma'am, when we illuminate the sample or the material, within the illumination region, with only this time, till now we shine the laser. From there is a thermal expansion.
Okay, and then does it have a memory? Suppose I switch off my laser, what happens?
When we off the lasers, uh, for some time, exactly time can I tell?
And that will be all. Thank you, Priyanka.
Ghosh,
Okay.
Professor Ghosh, are you?
Thank you, ma'am.
Yeah. And so you should keep your presentation on, otherwise. So can you go back to your this model that you were showing? So do you have that? Can you give a physical explanation of the adaptation that you have done in the model?
So slide is visible?
No, it's not. So that's what you should keep it on, right?
Okay, sir. Okay, sir. Sir.
So can you tell otherwise that yeah?
Yes, sir. Yes, sir.
No, it is.
Sir, question can.
I think it was towards the last few slides. Yeah. So
the theoretical formulation.
Yeah. Maybe make it bigger. So can you explain that what is the basis of this model? So there are some complex Lorentzians coming in the denominator. What is the basis of that? And what adaptation did you do?
So basic of this theoretical model is that in the existing equation, this is the nonlinear phase shift, and in the present model, we take the phase shift is a complex in nature. Here, real part corresponding to nonlinear refraction image.
What is x in the denominator here?
So x is a position.
Position, right? So you see that the denominator there is a kind of a complex Lorentzian x plus I pq plus 1, right? So it is like, so how does it come?
This is a transmittance equation. That's a nonlinear transmittance equation, and S is a position.
So because it eventually it gives a Lorentzian kind of deep, right? So eventually all.
So Gaussian. Yes, sir.
What is the Gaussian coming here? Can you show any Gaussian function here in this model?
Sir, Gaussian, when we move sample across the tightly focused Gaussian beam.
No. I'm not asking that. I'm saying that. So this model, you talk about transmission, right? So
yes, sir.
So where is the Gaussian function coming? You said that something Gaussian. I don't see any Gaussian here. I can see some Lorentzian kind of thing may come if you take the mod of that.
So we perform Z-scan measurement and we move the sample across the tightly focused Gaussian beam, and
that
from
is fine,
there.
but that does not matter. So you are normalizing the intensity, right? It's normalized.
Okay. Yes, sir. We normalize the intensity. Right.
But the shape that is coming, you can see that it's like a resonant shape, right? It's like a Lorentzian kind of thing, and your model would also suggest that you have a complex Lorentzian in the denominator. The problem. My question is that what is the physical basis of that? If you could explain, and what is the modification that you have done in that context?
So this equation we get from Bingju's papers, where they use the Gaussian decomposition method, where P and Q is a different Gaussian beams.
Right?
Yes, sir.
When you model something, a transmission like that, it is like a response function modeling, right? So it is not question of decomposition. So you have something you decompose, it's not like that, right? So what is the source of this model? That's what we want to understand. Right, you understand, right? For example, we are talking about the resonance. We model the resonance to a ramp-driven oscillator, and the response function will come like a complex Lorentzian. So just like the transmission is like that response function.
Okay.
So what is the basis of this equation and what modification you have done? That is the question.
So we only modified the nonlinear. We only replaced the nonlinear phase shift, which is complex in nature. We only replaced the nonlinear phase shift term from here.
I think Priyanka think over it actually.
Okay, maybe it's already a lot of time lost. It's not an answer, I would say that.
Sorry,
Dr.
sir.
Dr. Verma, you have any question?
Yeah, I have a very quick two questions. See, Priyanka, you have shown closed aperture Z-scans, and you have shared that there is a switching of your nonlinear refractive index, right?
Yes, sir.
Right. So can you explain why that switching occurs from
peak
valley to valley peak?
Yes, sir. In our work, when we see this sign reversal,
Yeah.
we explore when we explore the linear property. We observe defect state is present in S1 film. From this defect state in S1 film, there is a oxygen vacancy presence. So we can say that the oxygen vacancy consumes a space, and it gives
No,
rise
see,
to
this is a
negative.
this is a nonlinear optical phenomena, right? So
Yes,
you
sir.
have to correlate whatever you are talking. Right now, you are talking with the oxygen defect levels, and they are causing this optical nonlinearity. So
Yes, sir.
is that correct?
Magnetic origin, that is correct only?
Yes, sir. Oxygen in the presence of defect state, the open spaces, because of open space is a contraction is there in the illumination region, and we can see the
Did you
negative.
observe similar studies in nonlinear absorption? Like, for example, saturable absorption becoming reverse saturable absorption. We should have tried to see those types of switching also. Did you see that happening?
Sir, we see that reverse features in also open aperture Z scan curve, but not in this material. The
No, but
system was different.
here you are showing switching of N2.
Yes,
So
sir.
I believe you should have also tried seeing the beta values. I mean, how the
How the
nonlinear approach. Yes,
absorption properties also can be done,
right.
sir.
And
Yes, sir.
in the phase analysis of your films which you have grown, right? Those XRDs, what is the phase of your material? What is the crystal system to it?
Sir, Cr2O3 rhombohedral phase.
Okay, and the other one, nickel?
Nickel oxide is cubic phase.
So cubic phase. I mean, if you see from the crystallographic point of view,
Okay, sir.
which one will be showing the nonlinearity?
Sir, experimentally both materials
See, when we
showing
are
the
talking about optical
uh,
nonlinearities, we talk about some crystal structure and some symmetry and all those things. So this
okay, sir.
nickel oxide or materials, you are saying that is a cubic system.
Yes, sir.
So will it show those types of nonlinearities?
Yes, sir. This is the nickel oxide's nonlinear curve.
So is there any connection between the structure or your system and the
Sir,
nonlinearity?
we only see the nonlinearity in the
So this is the third order.
cytosolic.
So you will see it. What about any other?
Professor Tata, you have any question?
Yeah, just one question. Yeah. Just one quick question. What is the role of magnetic field? Because you did a nonlinear measurement using jet scan
Yes, sir.
in the
In the
presence
presence
of
of mag.
magnetic field.
Yes,
But
sir.
I have not seen what is the role of magnetic field here.
Switching was there, reversing was
Sir,
not.
in the presence of magnetic field, we can see the sign reversal due to the magnetic field. In the absence of
So,
magnetic field, the negative nonlinearity occur. In the presence of magnetic field, we observe positive optical nonlinearity. So we
so
can
what is
switch
that
with the
changes? You can
we can
switch the.
nonlinearity with the applied magnetic field.
Okay.
I think
Okay,
Yes, sir.
thank you.
we have to go
Yeah.
back to Priyanka. Please close it. Thank you, Priyanka.
Thank you
Abhishek
so
is
much,
there?
sir.
Yes, you have to ask. Please, Dr. Tata, can you ask your question quickly to Abhishek?
Han, Abhishek.
Abhishek is in the line now. Priyanka, please close it.
Abhishek. Yeah. I was asking the role of dislocations. Okay. You said dislocations are very important here. Okay. To know really the dislocations play an important, usually it doesn't. But here you are saying that dislocations are very important. So do you suppose if I change the substrate instead of sapphire to make the dislocations?
Yeah.
Do you see it plays an important role?
Yes, sir.
I reduce the
Obviously,
dislocation density.
yes, sir. Obviously, substrate plays a major role. If you have a lattice match substrate, that means if you can grow it homoepitaxially, GAN on
Yes,
top
sir.
of
Then
GAN.
you will not have dislocations, right?
Yes,
So
sir.
did you study that?
Yes,
To
sir.
say
This
that
is,
really dislocations play an important role.
yes, sir.
I have not seen that result. That's why.
So that is not included in my this work. This work is on gallium sapphire only. So now
Okay.
I am procuring some GAN templates because epitaxially is the only possible gallium nitride. Bulk GAN crystal are not available. So though growers have to grow on some foreign substrate only by heteroepitaxy. So one thing is that you can procure or grow GAN on sapphire, then take this as template and then GRAN on top of that. Then only you can be able to avoid this lattice mismatch part.
My second
Because
question is,
growth of bulk
if you keep more and more gamma, the radiation damage on the detector, you say it is not there, but I expect the radiation damage to take place on your material.
Yeah, cumulative dose.
Certainly,
Not,
sir.
Yeah, cumulative.
But the displacement energy of gallium nitride is higher, so damage is less. Mostly point defects are created, and those are recoverable within a day because they can move using the thermal energy of the ambient room temperature energy that is sufficient to move them to their original real state. So they make some complexes, point defects, and then if the thermal energy, they will get back to their minimum energy position. So that's why the dislocation effect is less. Because
Professor
number
Ghosh?
density is less.
Okay.
Professor Ghosh, your time is very short. Professor Ghosh, are you there?
Yeah, no, I don't have any further questions.
Dr. Sucharita Sinha?
I have just one question for Abhishek. Abhishek, why did you choose to use commercially available samples of gallium nitride for your study? Why not your own in-house fabricated samples?
Ma'am, we have also grown samples there, but the thing is that because the dislocation is so high there, the background doping is coming around 10 to the power 20 per centimeter cube. So in the presence of such high doping, electrical, that means you cannot make some rectifying junction, because if you generate some photoelectron, you need to separate out them. But
So why do you get so many dislocations in your sample as compared to, means you are nowhere comparable to the commercial one, you mean to say?
Optically, and in some part we are going towards that, but still we need to improve to go at least 2 order improvement, because now
Okay, Abhishek.
Dr.
Okay,
Bharma?
Abhishek, all the best.
Dr. Bharma?
Thank you, ma'am.
Yeah.
Sunil?
Abhishek, I was talking about the dislocations. What type of dislocations are you talking?
Actually, in literature survey, we have found that both screw and edge dislocations are available in GAN. And what we have done here, we have estimated these two dislocation density from RRCAT, from the FWHM of 002 and 102 scan. From there, we evaluated the dislocation density of screw and edge.
And what is the dislocation density you get in your sample?
Yeah, so it is of the order of 10 to the power 9 per centimeter square.
Okay, these are the commercial samples you are talking.
Yes.
And in the samples grown in your lab, what was the dislocation density?
That comes around 10 to the power 11, 10 to the power 12 order.
Okay. Yeah. And is there any other technique which you know which can give you a better maps of dislocations?
Yeah, I think around 12 o'clock can you tell them? 12 o'clock we can meet. Please.
To image it by cross-sectional TEM, then you can go there if the dislocation profile. Yeah. So that one image I have shown there also. Other than that, from top surface also, by using conductive AFM method, you can just count those seats, and from there you can.
Dr. Bharma, we have to stop it here. Next session.
Thank you, Abhishek.
Abhishek, I think after 15-minute gap, to all the judges, 12 o'clock we can meet.
Sure.
Other judges also, please take a break, and at 12 o'clock we'll meet all the judges in the other platform that is provided. And please check your email yesterday night. If it's not checked, I've compiled all the reviewer marks earlier, all the reviewers, please. So we'll meet at 12 o'clock, please. Please take a break. Thank you all for all the time. Thank you, this is closed now.
So there are no presenters remaining.
Sorry, so this same link we'll use, this link?
And we also thank all participants of this session for presenting their work in NLS-30. So this brings us to end this session.
So their last presentation is not there, this Chandrakanta Singh?
Next session will start at sharply 11:45 a.m.
Yeah, Dr. Bharma, yeah, he's not well actually. He told that he's not presenting.
Fine. Okay.
So that was.
We have 6 presenters.
So will we use the same meeting link?
No, other link is there because there all the other research scholars cannot come there. Only the judges should be able to come there. Separate link is same. So around 12 o'clock we'll meet that. Okay. If there is a problem,
Okay.
please take it. Thank you very much.
Okay. Yeah.
Thank you.
सर चेक कर लीजिए सर, ये लाइन चेक कर लीजिए।
Hello, you can hear my voice?
Yes, madam, we can hear your voice.
Okay. Okay.
Yeah, thank you.
বোর হয়ে গেছি, মার্কস নিয়ে লাফালাফি করবে। আমি মার্কস দিয়ে পাঠিয়ে দিয়েছি আলো।
मुझे क्या बोला? हाँ, वीडियो पे J5 कैप्चर है ना? नहीं, J5 आपका वो है क्या? हाँ, आगे दिखाऊं ना आपको? दिखाऊं मेन स्क्रीन पे? इतना काफी। यहाँ पे एक बार देखना है।
Hello everybody. We welcome all the participants, all the dignitaries in this last but one session, which is on applications of laser in chemistry, biology and materials. So this is going to be very interesting session, and this session will be chaired by Dr. Lalita Dhareshwar. Dr. Dhareshwar has done her BSc Honours in Physics from Bengaluru University in year 1969, and she joined BRC through 13th batch of training school. She did her PhD in laser and plasma physics in 1988 from Bombay University. Dr. Dhareshwar has also worked at renowned international institutes like University of York, UK in November 2007, PN Lebedev Physical Institute under the ILTP collaboration in 87 and 2007, Institute of Plasma Physics and Laser Microfusion, Warsaw, Poland in 2005, Prague Asterix Laser System, Czech Science Foundation, Czech Republic in 2007 and 2011. Her specialization is in the field of high power picosecond and femtosecond ND glass lasers, physics of high temperature, high density laser plasmas. She has made important contributions in the fields laser driven shocks, physics of inertial confinement fusion, and laser plasma as an intense X-ray source. She has also worked in generation and studies on matter at megabar pressure and keV temperature using high peak power ND glass lasers with picosecond and femtosecond pulse duration. She has published more than 75 publications in international and national peer-reviewed journals. Over to you, Dr. Dhareshwar.
Thank you, Dr. Asavari, and thanks. I thank you a lot. Thanks a lot for inviting me to chair this session. And today we have come now to the very last session of the NLS technical session. I mean, after 3 days of exploring the new and wonderful dimensions in the various fields where lasers are being used to take us into new frontier areas. And in this session today, we have 3 talks on 3 diverse applications of lasers in the frontier areas in chemistry, biology, and materials. So the first talk is by Professor Ranjini Vishwanatha on the title of the talk is Magneto-Optical Effects in Doped Quantum Dots, which is a fantastic and very interesting topic. And before she starts giving her deliberation, I would like to introduce Professor Ranjini from JNCASR, Bangalore. Dr. Ranjini Vishwanatha is from Jawaharlal Nehru Center for Advanced Scientific Research. She did her PhD at the Indian Institute of Science under the guidance of Professor D.D. Sharma on the growth in solution and electronic structure of nanocrystals. Subsequent to her PhD, she worked as a postdoctoral fellow at Professor Xiong Kong Peng's laboratory at the University of Arkansas at the Los Alamos National Laboratory in Professor Victor Klimov's group before joining JNCASR. Her work revolves around some interesting behavior of transition metal dopants in nanocrystals, qualitatively different from bulk. Her work has been published in leading journals, and she has been awarded several national awards like SERB Power Fellowship, Karnataka State C.V. Raman Award, MRSI Medal, DST Young Nanoscientist Award, Sheikh Sakr Fellowship, the INSA Young Scientist Medal. She is chosen as a Young Associate of the Indian Academy of Science, founder member of Indian National Young Academy of Science, among many others. She is also a reviewer in many leading journals and has given several talks in leading conferences. And today she'll be speaking about magneto-optical effects in doped quantum dots. I welcome Professor Ranjini to the podium and take over. And I would like to tell you that you will be given a warning bell at the end of 22 minutes. And the final bell will ring at 25 minutes. And another 5 minutes are devoted for questions and answers. So I request Dr. Ranjini Vishwanatha to start her lecture.
Thank you, Professor Dhareshwar. And at the outset, I would like to thank all the organizers for inviting me for this presentation. I hope all of you are able to see my screen. I'll put it in slideshow mode.
Yeah, we are able to see the screen.
Yeah. Slideshow mode is visible?
Yes, it is visible.
Okay, so let me get started with the talk. Today I'm going to discuss about the magneto-optical effects in doped nanocrystals. Before I get started, I would like to thank the people who did this work. This was done by one of my students, Ms. Mahima Makkar, who is now graduated and since then left the group. And I would also like to thank all the collaborators and the funding agencies involved in this work. So before we get started, let me give a brief outline of what I would like to look at. I'll give a brief introduction to magneto-optics because magneto-optics not being that commonly studied. Then we will look at a couple of aspects of wave function engineering and looking at circular dichroism in absorption and in photoluminescence. And most importantly, the more recent results on this magneto-optical Stark effect. So basically, when you look at absorption in magnetically doped nanocrystals, what you see is in a non-magnetic semiconductor like zinc selenide, cadmium selenide, any of those systems, you will have just the excitons, and when you excite it with some external magnetic field, there is corresponding internal magnetic field that arises because of this exciton coupling. And you see that there is a small internal magnetic field. But in presence of a magnetic, one or two magnetic ions, you see that there is a strong magnetic field, internal magnetic field that is generated because of the alignment of these magnetic ions. And that is what we are going to trace. So if I were to look at the absolute numbers, so this depends on, of course, the applied magnetic field, which is of the order of 100 micro EV per Tesla. However, these fields are dependent on the SPD coupling interaction that happens between the magnetic ions and the host semiconductor, giving rise to huge splitting of the order of 1 EV. So we are talking of a difference in about 6 orders of magnitude. And also the other interesting aspect is these fellows are independent of temperature. You can see the splitting irrespective of whatever temperature you do. But this exciton Zeeman spin splitting arising from the exchange field is heavily dependent on the temperature. So much so that effective G factor can go up to about 1000. This is what we are going to study in these dope nanocrystals. Specifically, I am interested in looking at what is the effect of these Zeeman splitting when you vary the confinement. Is it dependent on the confinement? Because that is something that has not been extensively studied. So how do I measure this? The direct measure of the Zeeman splitting can be obtained from circular dichroism, wherein you measure it with polarized light and a left circular and a right circularly polarized light, and the difference spectrum gives you the is a measure of the Zeeman splitting. So this is what we're going to look at. We're going to look at Mn2 plus doped CD-ZNSE nanocrystals. And the reason we have this CD-ZNSE is because when we have only ZNSE, the nanocrystals are just confined within this core. Now we slowly expand this confinement in the holes so that the electron is confined in the zinc selenide and the hole is confined to the cadmium selenide, and we can now play around with the confinement of these nanocrystals. The size of all of these nanocrystals are approximately similar, except that the band gap changes because of the composition variation. Now let me look at the various Zeeman splitting. Before we begin, I am going to look at zinc selenide, cat selenide itself, because just to give you an idea how it would look like. Irrespective of whatever is the cat selenide shell thickness, it will be the same almost. You can see the thin shell and the thick shell at various temperatures, more or less exactly equal and linear as a function of field. Now, this is expected as there is no exchange interaction. Now I introduce manganese, about 1% manganese, not a huge lot. And we clearly start seeing the effects of the SPD exchange interaction. This is one of the very core of definition of the nanocrystal being indeed the manganese being core dope, because only if it is doped properly without any manganese interaction do you see some exchange interaction like this. And this can be actually fit by a Brillouin function, and you can see that this clearly fits the curve for the various temperatures, and you see that the Zeeman splitting is of the order of 4.8 MeV. Now, my interest was not just to see what is happening here, but what happens if I change the confinement. How do I change this confinement? That I've already discussed, that I'm going to introduce this cat selenide on the shell, and that spreads the wave function. So now if I decrease the confinement, you can clearly see that as a function of decreasing confinement, two things are happening. One, the position is changing. That is not very surprising because this is where the band gap is, because I'm changing the band gap by changing the confinement. But more interestingly, you can see that the one with maximum confinement has a lot of intensity, and as you keep decreasing the confinement, the MCT intensity also decreases, which means the Zeeman splitting also decreases. That is actually quite surprising, because so far there has been no evidence of the decreasing Zeeman splitting because of the confinement, or rather the with increasing confinement, the Zeeman splitting increasing. So this suggests that a large MCD with Zeeman splitting saturates. There's a strong temperature dependence. That's not surprising. But there is also other dependencies. Like, for example, you have this 1% manganese, 2.5% manganese, 5%. You can ignore the 10% because by 10% I have manganese interaction, and that's why you can see that the SPD exchange interaction is not very strong and it's very, very tiny. But within this various 1%, 2.5%, and 5%, you can see that the confinement actually keeps increasing with increasing, the Zeeman splitting increases with increasing confinement. The absolute number, not the negative. The negative comes because of. So basically what I've shown here is that Zeeman splitting changes with the number of manganese ions per nanocrystals. It changes with the quantum confinement, and it also changes with the growth parameters. Not that much sensitive, but when we see how fast this changes, you can see that it can be engineered. What am I engineering by growth is basically I'm engineering the position of the manganese ion, because when I'm heating it, the manganese ions tries to diffuse out. And if the manganese is in the core, you see a particular Zeeman splitting. And as it starts diffusing out into the shell, you can see that the manganese ion is again interacting and the confinement changes. So it is not changing a lot. But what we can see is synthesis parameters by which I can change the radial position of the manganese ion, the number of manganese ions, the confinement. All these play a very important role in determining the Zeeman splitting. So why is it important? Why is this Zeeman splitting important? What do we see from this? So in bulk systems, this was all that was observed, not very much interesting. But when we look at the, for example, when we look at the photoluminescence, you see that there is a bandage emission here, and there is a manganese emission. This is a typical bulk spectrum. And you can see that when I apply a magnetic field, the manganese in both directions dies very quickly in the order of 2 Tesla or so. And the bandage, one of them, obviously it is very polarized. So one of them is growing very strong and the other one is very, very weak. So this was what was expected. This is not very surprising. So the manganese emission dies very quickly in both directions. One direction the bandage dies, the other direction the bandage increases. Now, what was interesting? Basically, the understanding that people had at that time was that you can actually, manganese is a forbidden emission, and still it happens. How does it happen? So they say that because these excitons, the conduction band and the valence band exciton, recombine non-radiatively and give that energy to the manganese so that it can radiatively recombine, and overall spin is conserved. Individual spin is not conserved, but overall spin is conserved. So in this way, if I do that, at B equal to 0, there are 16 possible transitions for which the manganese excitation is possible. However, when I go further and I see this, when I apply a magnetic field, the conduction band and the valence band is heavily polarized. They cannot compensate for the manganese change of spin, and because of which the band you don't see a manganese emission. This was the understanding in bulk spectrum. This specific understanding itself is questionable, but that's not the topic of today's discussion. So I'm going to go over what happens when there is strong quantum confinement to these photoluminescence. The first thing that happens is when you see this, when I go to low temperature, I do not see any band edge emission, unlike these bulk systems. That is okay, because given that there is a very strong confinement, maybe we would see the band edge emission at a later, it's very weak. But when I apply the magnetic field, I still should see the same spectrum that I saw for the bulk system, because qualitatively nothing has changed. And then I should see that the manganese emission decay, and then the band edge emission should come up. But surprisingly, not only does the band edge emission not come up and the manganese does not decay, but a basically forbidden emission is observed, that actually it is polarized, heavily polarized, and not only in terms of intensity, but band edge emission never comes up, and it follows, the intensity follows exactly the same profile as that of the MCD that we just saw, which can be actually mapped onto the MCD by a single multiplicative factor. And very importantly, this manganese emission, which is basically a forbidden emission, is polarized. That suggests that there is some kind of an interaction that is happening at this stage when you have a confinement. What we believe, our current understanding, is that basically this manganese emission can happen to be polarized only because there is an excitation process that is very that is not that is spin allowed, and that is extremely fast. And when the band edge excitons are polarized, the excitation of the manganese ions are also polarized, so the change of spin, which is the emission process, will also become polarized. But all these are interesting, very interesting. However, my main concern with all this is I'm looking at, as you can see, the typical temperatures I'm looking at is 1.54 Kelvin, 10 Kelvin. And you can see by the time I've reached 20 Kelvin, it's almost dead. So if I want to look at any real life applications, I need to have something that is at room temperature. I need to have an polarization at room temperature for any spintronic applications. That is where we started looking at other signatures, if there were any, and that is where we look at magneto-optical Stark effect. This was a term that was coined by us. So let me first explain to you what is Stark effect. Stark effect is basically when you apply an electric field, there is a shift in the energy levels. As you can see here, so when you apply an electric field, there is a shift in the energy levels. Because of the shift with and without pump, you can see that there is a transient nature that you can observe. Very importantly, this is present only in presence of for the duration of the electric field. So we found that people actually found that there is another variant of this, which people called it the optical Stark effect, wherein because of the hybridization between the photons and the electronic state, there is similar signatures that are observed, but again, similarly, it is transient in nature, persists for the duration of the pulse, and it later undergoes impact ionization. So you can have an electric Stark effect which is interaction of matter with electric field, or you can have optical Stark effect, which is the hybridization of the photons with the electronic states. And the signature of both of these is that it is only present for the duration of this whatever is the external field. It's not an internal phenomena. Now what we observed is, what is this magneto-optical Stark effect? I wanted it, these are ultra fast durations. So having it for an ultra fast duration is as equally not so useful as having it at 4 Kelvin. So what we did do is use the use these dope nanocrystals, and we see the spin up excitation is very different than the spin down excitation. For example, the spin up excitation is relatively unhindered, and spin down excitation is changed by a given energy, giving rise to two states. So basically, this is the excited state dynamics that you are seeing. You have the spin up, which is unhindered, and the spin down, which is hindered. So basically, again, you see a difference in these two states, creating basically two states, two magnetically inequivalent states, which can play a very important role for spintronic applications. So what we did was we took Fe doped nanocrystals. These are some basic characterization to show that they have been indeed formed and nicely from the XRD and the XFs, and the absorption onset is typically around 2.45 eV, like that of most serious nanocrystals. So why did we choose iron? Iron is basically adds a new spin degree of freedom, so which means it has new effects, new capabilities, and most often iron has a single spin state because it's a D6 ion. So the presence of multiple spin states is always interesting because which are energetically accessible. They cannot be very high. At room temperature, they should be energetically accessible. Then they can be very important in this thing for spin states, spintonic applications. And iron fit very nicely into that category. And we also observed that from the literature, there were signatures that said that in presence of magnetic field, it can give rise to some spin splitting, and because of which we thought iron is actually a very interesting system. So why CDS? We could have chosen any other system. The very important thing is these CDS, these are not any random CDS nanocrystals. These were CDS nanocrystals that we prepared specially so that they could, we needed to make sure that there are no other defect states, because defect states can easily override these small effects which are otherwise not visible in presence of these defect states. So we wanted a very defect-free nanocrystal. So what we did, we checked the transient absorption. You can see that there is an initial decay of about 10%, following which there is literally no decay for the period of our observation, which is about 1 nanosecond. So which means there are very long-lived excitonic states. So except for the initial fast decay in the first few picoseconds. So let's see what is this initial fast decay, because that's also important. What happens is most often we look at images like this, but in real life, this is not what we see. We will be literally looking for things like this, wherein every the surface states, chemical environment, everything tries to kill the luminescence based on this non-radiative decay pathways, and which is what we need to override now. And for that, what we did try to do is that we looked at what is this fast pathway, and we see that when we look at various energies, we see that at very higher energies there is no there is a huge decay, but there is no growth time. Whereas at lower energies, more typically closer to the bandage excitation, remember these are about 2.45 eV band gap, you see that there is time taken to grow for these. And if we actually try to fit these systems, we see that this decay corresponds to exactly the time that is taken for these systems to grow. So what we are talking of here is these higher excited states are decaying to the first excited state in the order of 650 to 700 femtoseconds. And this is not a non-radiative decay, surface state, defect states decay. And they can actually easily be plotted and seen that the growth can be accommodated at the cost of the decay. So basically that 10% decay is not from the surface states, and post that it is extremely flat. So this is what was interesting for us, and that is where we started looking into these systems. And there is no intraband cooling, there is no non-radiative relaxation, which means there is no defect states. So now we looked at these systems with iron doping, and we see that with iron doping, suddenly it quenches very quickly. You can see how fast it is quenching within the same time scale, and this is the expanded region. And you can see that this is actually what it is doing. There is an absence of bandage luminescence. It's quenching so quickly. You can see that it's quenching quicker than that of the growth of the CDS. So it kills the photoluminescence, and that's well known, the acceptor states by Fe. But what exactly is this Fe doing? Now luminescence is gone, that's okay. But when I look at the spin selective interaction, I can see that the spin down state is some very different interactions compared to the spin up state. In the spin down state, the hole is localized in the host, and the electron is localized in the iron atom, whereas in the spin up state, both electron and the hole are localized within the host. So this allows for a decay through the bandage states, and this one allows through the iron state. So basically you're getting two different iron states. You can see that the mu B is also different here. This is 2.56 and 3 Bohr magneton. So this gives us spectral signatures of this stark shift, which we can observe in the TA. And as you can see, with increasing iron percentage, you can see that it's dying, and with no iron, there is no such derivative-like feature. And this feature persists at all times measured after the excitation. It has reduced, true, but it has not gone even at 1 nanoseconds. If that is indeed true, then the question that actually the referees asked was, you should see this in circular dichroism without the magnetic field. So which is what we did. We did circular polarized TA, and we see that there is indeed a signal, quite a strong signal at all times. They persist at all times, and this is not even due to the biexcitonic effects. And this suggests that actually that this is a very interesting phenomena which has been newly observed, and it is very specific for single interaction with single iron, meaning there should be no iron-iron interaction. This is just a theoretical calculation to show that if there is indeed iron-iron interaction, then all this is damaged. You don't see any such spin-dependent phenomena. So to come towards the end of my talk, the magneto-optical Stark effect was observed for the first time, and Fe-Fe interaction dominates, then you don't see it. It's a long-lived and much stronger than the best reported shifts of other Stark effects. It's observed for the first time, and it's an internal perturbative field produced by magnetically active Fe. And under resonant conditions where you don't have this excited states to provide this difference in spin, you do not see this. And thank you.
Thank you, Dr. Ranjini, for this very, very interesting talk. Now the talk is open for questions. If anyone wants to ask a question to the presenter, please go ahead. We have 5 minutes for that, for this question answer session. Well, Dr. Ranjini, I would like to ask one question. Using these doped quantum dots, what are the applications that you are envisaging? Either in your lab or maybe it could be in some other lab, but I'm sure there would be very exciting applications for this. So I would like you to tell us, I mean, something about what are the
So,
applications.
the first thing that we are looking at is to see these spintronic-like applications. Because if the two spins are behaving differently, true, I still have a ways to go because now I've only shown up to 1 nanosecond, which is better than 4 Kelvin, to be very frank, but still 1 nanosecond is still a very short time. So if we can have these applications for longer time, then any spintronic-like applications can be very useful. The second application that we are looking at is polarizers, which we are actually actively trying to collaborate with the company and try to work out a quantum polarizer with these doped nanocrystals, especially when you have two different spins interacting in two different ways. And the other thoughts that we have with these collaborators that we are working with is, kind of random number generation, quantum random number generation and things like that for two different spin states. Because these spin states, which one is accessed is quantum mechanically not known. So you can, so they have very large number of applications in army and those kind of systems.
Can it be used? Can they be used for some kind of a very fast frequency filtration, component in a certain experimental setup, where you want to kind of only choose a certain frequency for a very short duration?
That is possible, provided that your frequency differences are like of this order. I'm looking at energetically accessible spin states. So which means that the difference in these are typically of the order of 25 MeV. Not very much large, because then I cannot access it through this these kind of just by excitation with a pulse or something. I need to be able to access these states through whatever excitation that I'm providing. It may be a laser pulse, it may be whatever. So your frequency difference that you're looking at should be, I mean, you should be really able to distinguish between these two frequencies.
That's right. Yeah. Good. Very nice. So any more questions, please?
Yes, I just wanted to ask one question. Madam, what is the duration of the laser pulse that you are using currently? And
these are femtosecond duration.
Yeah.
25 femtoseconds, 25 to 50.
Yeah, and the longest time that your exciton lives on is in nanoseconds, right?
1 nanosecond, that's the duration. I mean, that's the instrumental this thing that we have. We cannot measure it more than 1200 picoseconds to be very accurate.
And the temperature now where you're operating it, because the
room
reason you
temperature.
went, okay, because you shifted to your magneto-optic.
Yeah, so the reason those were at low temperature, the Zeeman splitting and all these are observed at low temperature only. So we wanted to see something at room temperature. So these are all room temperature measurements.
Thank you, ma'am.
So if there are no questions, we still have 1 more minute. So in case anybody wants to go ahead and ask a question, or shall we proceed ahead? Okay, so thank you very much, Dr. Ranjini, for your very interesting talk, and all the best to you for your future research. Thank you very much.
Thank you.
So next talk is by Dr. Sunita Kedia on enhanced functionality of metallic biomaterials using pulsed lasers, which is a very, very interesting area in biomedical applications. So she is going to talk to us how the implants for various applications can be modified or treated by the surface modification using lasers. And Dr. Sunita Kedia has done her PhD in demonstration of microcavity lasers using photonic band gap materials from IIT Bombay in 2011. She worked as a postdoctoral fellow in PRL, Ahmedabad, in the field of optical trapping of microparticles. Before joining BARC as KSKRA fellow in 2013. Since then, she has been working on photonic bandgap materials, laser-induced surface texturing, and biocompatible materials. She has about 30 publications in peer-reviewed journals, 2 book chapters, and about 25 conference papers. Her current research interests are laser material processing, thin film coating by pulsed laser deposition, and selective laser sintering. Today, she's going to talk on enhanced functionality of metallic biomaterials using pulsed lasers. Please, Dr. Kedia, please go ahead.
Thank you, ma'am. First of all, I would like to thank the organizing committee to give me this opportunity to present my work here. I am from infrared laser section, LNP.
Hello, Sunita, can you please talk a little louder? It's a little low. Yeah, please.
So I am from infrared laser section, LNPTD BARC, and today I will talk on enhanced functionality of metallic biomaterials using pulse laser. These two images here are indicating the importance of this work. In early ages, before centuries, a damaged tooth or a missing tooth used to be replaced by this kind of cells or sometimes stone. But nowadays, with the development in the medical field, such substitutions are doing in a very sophisticated way in this form. So before going to these details of this work, I would like to spend a minute saying what my section is engaged in, what we are doing actually. So we are working in both directions. We are in research and development and also in application. So in R&D, we are making CO lasers using cryogenically cooled CO2 laser gas mixture. We have expertise in pulse and CW CO2 lasers. We are doing synthesis and characterization of different laser dyes as per divisional method. In application, we have done isotope separation by molecular approach, and we are also doing surface modification of biomaterials. All these works have been presented in the form of different posters, and the posters numbers are listed here for those who are interested to know more. I will talk on surface modification of biomaterials. So in next 20 to 25 minutes, I will discuss what are biomaterials, how an implant failure can take place, and what is osseointegration, techniques for surface modification, laser-based surface modification of biomaterials. Then I will discuss some results of picosecond laser-treated titanium, 6 aluminum, 4 vanadium bioalloy, and pulse laser deposition of zirconia on this biomaterial. Finally, I will summarize the work. So before this, first of all, we will see what is the biomaterial. Material which can be used for any period of time as a part of human body, which can treat, boost, or replace any tissue, organ or any function of the body is known as biomaterial. There are few examples such as dental screw, scaffold, this skull scaffold, spine, kneecap, and jaw, and some connecting plates, which is also known as reconstructive plate. So nowadays, with the modernity in the medical field, every part of a human body can be replaced, and we know how the youngsters are getting fascinated towards the cosmetic surgery. But everything available in the nature cannot be fit inside a human body, and the material which is chosen as a biomaterial has to satisfy some properties, such as the material should be a biocompatible material. It should remain chemically inert in all conditions and should have a similar mechanical properties with the as of that organ which it is replacing, and it should be non-toxic to the body. So the biomaterials are basically divided into 3 parts. Bio-inert, the material which does not interact with the body. There is no chemical or physical interaction with the body, but the material will be biocompatible. It will allow to grow bone like apatite or tissue on its surface. So those materials are bio-inert. Metallic biomaterials are coming into this category, bio-inert materials. The second is bioactive. These materials takes part in osseointegration, means due to with ion exchange, these materials can give donate some ion and accept some ion, and they can osseointegration and also integrate with the body. And there are some biodegradable materials which are relatively new, and these materials are capable of decomposing and getting replaced by the body, and it will just flush out from the body. So there are various metal, alloys, ceramics, polymers, and composites are available, which are already chosen and are in use as biomaterials. So if so many materials are already available and are in use, so what we are doing? What is our role? Uh, it is shown that with the available advanced tools and very like advanced medicine, sometimes it is happening that the artificial implant is getting rejected by human body, and this rejection can be done can happen within few months of the post surgery. And the reason for that rejection is maybe due to surgical trauma, poor osseointegration, bacterial infection, or so on. So I have shown an example of poor osseointegration of dental implant, where the this osseointegration was not good. So again, the second possibility is the problem arise over the time, and due to insufficient bone volume, progressive change in the loading, that is the weight of the patient, if it is increasing over the time, or prolonged micro movement, if the osseointegration is not good, then there will be always a micro movement between implant and the body tissue, or generation of fibrous tissue around the implant area. The implant can fail, implant failure can occur after 10 years or later, and this is known as late implant failure. This is an example where fibrous tissue has generated on the implant area. So all these complication leads to resurgery and implant replacement. But this is again a very costly and painful process, and some patients with their health condition may not allow or may not go for the resurgery alone. So the main aim is to increase the lifespan of the implant in human body. In present scenario, the lifespan is in between 10 years to 15 years. So this can be done. The interaction of the body of the implant with the body has to be improved by functionally by changing the, and it is they reported that this functionality or this interaction can be improved by changing the surface properties of given implant. Because surface of an implant is the first part which is seen human body after implantation. So that is the part which is the interacting very first minutes to the body. So to understand it further, let's see what is osseointegration, how the implant is interacting with body, and it is why it is very important. So osseointegration basically is a very complex process. Many things occurs simultaneously during this process. But if I have to explain it in few words, so I can explain like this. Just after surgery, the first thing is happening, what happens is the protein absorbed on the implant surface. Those are the blood proteins available in the blood of a human being. So this protein decides whether the implant is suitable or not, and then after that, bone reabsorption and formation of bone matrix will occur. And once this will fix, the implant will fix. With time, over the time, the body will see how much force is falling on the implant, which is the direction of force. And with all this measurement, bone remodeling, the body will remodel the bone, where the bone has to be like more more density, and where so it depends upon which type of force is falling on that part of the body. So after remodeling, bone remodeling, tissue formation takes place, and this whole process we can say it happens within 8 to 12 months after a metallic implantation. To see it more closely, let us see this image. This is just a rough diagram where when an implant is going inside a body or in a bone, it sees this kind of surrounding. But for a cell of size about 30 to 40 micron, the cell sees the micro nature or micro roughness of this part. It is just seeing this micro roughness. And when the cell adhere, before adhering, the cell release some protein, and those proteins adhere to the surface, and then cell adhere to those proteins. So those proteins is the nano feature of those structures. So basically, the macro structure of the implant is not that important as the nano structure are important. So if this structure is good and the primary fixation of the implant depend upon the nano structure or addition of this protein with the implant. So the primary fixation, future bonding and lifespan all depends upon this surface feature of the implant. So in general, which can be known as surface roughness. So surface roughness or the average surface roughness of the implant can be of a material can be divided into macro, micro and nano, and all have their significant effect in all other parameters. So now we will see how one can change the surface feature of a given implant. If the implant is already available with us, how we can change. So there are basically two ways to change the surface. One is topographical modification. We will change the surface morphology. We will change the microstructure, roughness, everything. Or second is surface coating, where we can choose some material for desired application. We can coat the implant available with us. And we are basically doing both. We are doing topographical modification and surface coating also, and to improve the properties of existing implant. So for topographical modification, there are different ways: sandblasting, acid etching, chemical treatment, or we are using laser surface texturing. This is a typical setup for this type of modification, where the laser beam is directed and focused on the surface of the implant or the surface of the sample, and the sample is attached to a computer controlled XY translational stage. Here we can change power of the laser, the focusing condition. Here I have shown a cylindrical lens, but one can use spherical lens. We can change the focal length of the lens. And another important part is we can scan the sample as per the requirement, or we can optimize the sample scan speed. So all these factors play important roles that how the patterns will form on the surface of the material. For surface coating, different techniques such as chemical vapor deposition, salt gel, anodic oxidation, and other techniques are being used. And we are using pulse laser deposition technique. So this is a typical setup for pulse laser deposition, where laser beam is focused on a target, the target which is the material which we have to coat. At some threshold, the plasma formation will occur on the target and plume will expand in this direction. This is our target, and here is our substrate, which is the biomaterial we have to coat. And this distance is fixed, and this whole system is under vacuum. So here what we can change laser fluence. We can change our target in our system, our available system. We can put 6 type of different targets which we have to coat. We can make multi-layer on the surface of a sample by using different target materials. And the most important thing or very important part of this work is that we can change the substrate temperature during pulse laser deposition during the process. So the importance of surface temperature I will discuss in few of my slides. So today I will discuss both results of both surface texturing and very recent results of our surface texturing and pulse laser deposition. So let's see how this works. So there are 3 main parameters on which the laser metal interaction depends. So laser parameter, material properties, and experimental condition. However, there are many other factors which affects the process and also the final product very significantly. So this is basically the process, how much energy the material is absorbing from the laser, from the source, and how this energy is distributed, whether it is just restricted to electrons or to the lattice of the sample, and that will decide which type of patterns will generate on the sample surface. Since in our case, material is fixed, we are mostly using, here I will present results of only titanium, and experiment condition is also fixed. Our focusing condition is almost fixed, and it is in ambience. So I will discuss how the laser power parameters such as pulse duration, wavelength, and fluence, or sorry, peak intensity are different, how it is affecting. Here I would like to say why this laser surface modification is important. This is a contamination-free technique. It is a single-step, fast, reproducible, and it is confined to the focused volume of the sample. Contamination-free means that there are groups who are using chemical treatment, acid etching to surface with the biomaterial. Say, and sandblasting is another method by which the surface may get contaminated with some kind of. And then again, one has to follow the how to decontaminate the sample. This single step here, we have to directly irradiate the sample with laser, and we have heard a very good talk on lithography, femtosecond lithography, where the pre process and after lithography, post processing of the sample, will the whole process have many steps to follow. But here we will directly incident the laser beam on sample, and it will generate some kind of structure which may be useful or that we have to further characterize. It is confined to the focused volume. The modification will occur only in the focused volume on the sample. It will not affect the bulk property. So all the mechanical properties of the material such as young modulus, hardness, and everything will remain intact. And there will be change only in the very thin layer of the sample. So a metal contains lots of free electrons, and when a laser beam incident on this metal, the first thing happened that these electrons absorb the energy from the laser beam, and this is very fast, and that in the range of femtosecond. Electron absorb after absorbing energy, electron excite and collide with each other till they thermalize, and this process will happen within till femtosecond time. So, if the pulse duration of this incident light is still larger than a picosecond, then after thermalization, electron will start transferring their energy to lattice. The excess energy they will transfer to lattice. This will heat the lattice, and then diffusion of the heat to the surrounding will occur. So, the extent of this process of surface modification, is very much depends upon the pulse duration of the laser. And different groups have, therefore, for surface modification, all type of lasers starting from CW laser to femtosecond lasers are induced. And one has to choose the laser according to their material which they have to process. That I will just show in my next slide. Here we will just see that how this peak intensity of a laser changes with its pulse duration. This is a very rough picture just to see the difference between how it is changing. So if this red, we will consider this red curve, which is average power of a CW laser. For this kind of average power, a nanosecond laser can show a peak power in the range of megawatt. A picosecond can show a peak intensity in gigawatt. If we will reduce the pulse duration further in the range of femtosecond, the peak intensity will increase to thousands of gigawatts. So we have to choose which type of material we are using. If we are using some kind of biopolymer or ceramics or metals, then we have to choose our laser accordingly. Another very important factor of laser is wavelength. So here I have shown how the absorption of the material depends upon wavelength. Here we will see only the green curve, which is for metal, and we will ignore this brown curve here because this is for a non-metal and we are not going to discuss this. So for metal, the absorption is very high in UV range, and absorption reduced with wavelength, and it becomes very less in the infrared and far infrared region. Most of our work is in this visible variant where we are using laser of wavelength 532 nanometers. So since there are many parameters which can be changed starting from power, intensity, wavelength, and pulse duration, many work has been done with for surface modification of biomaterials since long. It is very difficult. It was very difficult to discuss all the available literature on this work. So I have chosen few which I found is important as a significant development in this field. So initially during 90s, the laser was used for heating and remelting of titanium based aluminum sample, where the major induced modification was for creation of this TiO2, titanium oxide layer on the surface of the material. And this titanium oxide layers work as very protective layer for those material for in terms of corrosion resistance. Sometimes they work for antibacterial behavior. The main aim of at that time was to increase the thickness of this titanium oxide on the surface of the sample and also the adhesion. During 2005 to 2015, laser-induced micro nanostructure has grown. Where using ultra-fast laser, scientists could generate very nice conical structure or different kind of island structure, micron size, which were covered with nano-size features on it. So those samples were showing very good results in terms of they were very super hydrophobic properties, antibacterial properties, and they allow very nice interaction with body. In last decade, additive manufacturing and 3D printing of biomaterials have developed, where very customized structure can be made. And that customization means individual. For individuals, we can customize the organ of that individual person and can be used in their body. So this field is means like evolving in various directions, but still there is not many surface modified implants which are used commercially. Of course, some in vivo tests are done. Animal trial and human trials are going on. But search for a suitable implant with short healing process, along with lesser dose of antibiotics, and long service life with possibility of mass production is still a challenge. So research needs more involvement and developing of new techniques and detailed testing. So let's see how is our journey in this and how much we have learned till now. So we started this work about 6 years back, and then we started with a nanosecond laser for surface modification of bioglass, titanium 6 aluminum 4 vanadium, and P16 NLS. All these materials are known as biomaterials. They have already used as biomaterials. So this is this is the same image of the sample where we could generate this type of microstructure, and we could see a very good growth of hydroxyapatite, that is the bone-like apatite which forms the bone between implant and body tissue. Within 1 day. This is for an untreated sample where there was no growth, but on this surface, and here we can see a very crystalline growth of HAP was found. Similar effect was observed in case of titanium, where we generated pattern structure, and it shows a very good biointegration, and there was no problem with its biocompatibility. This is the last year work where we have generated some group structure, and here we could align the cells very nicely. But a nanosecond laser shows heat affected zone, which the property of this zone is different from this area, so we cannot use this method for an actual implant. So we have also done with femtosecond. With the lack of time, I am just not discussing this slide. So here again, this is the results of the femtosecond laser, where we could do very nice growth of HAP on bioglass, and we could generate very nice conical structure on titanium on large area, and it shows antibacterial behavior and shape degradation. But again, the commercialization of this femtosecond laser was difficult. So since from in 2021, we prefer a picosecond laser, and this picosecond laser is very robust and required very less maintenance. And then it can be used very easily, and it has the ability to create equally good pattern on the surface of titanium as we have obtained from previous step. So these are some SCM images which we have created last year. Here, this discussion of this particular sample is there in one of the posters. So after making these surfaces, we have to do, actually we are in the process of checking all the samples for hydroxy growth, addition of protein, cell, antibacterial properties, corrosion and resistance. So here I will show some results of osseointegration, for which we have prepared simulated body fluid in-house by following some literature. And this kind of simulated body film contains same type of iron concentration as of blood plasma. So we made a different set of samples, like 10 samples of each kind, and we just immersed in the simulated body film for a different number of days. We could. It is difficult to show all the results, but here I have shown some STM images. In the initial days, only some deposition of some crystal structure was found, and the growth improved, and the morphology of the sample changed. If we characterize the sample, we show the laser treated area is showing very good crystalline structure of HAP on its surface in comparison to untreated sample. So, and the CFRBA by P ratio, which is the main reagent of HAP, was also in the required range. And other testing of these samples are in progress, like all testings we will do. Now I will give some results of second part, zirconia coated titanium. Zirconia is again a biomaterial, but it is costly. So use of zirconia, direct use of zirconia will be very expensive. But intrinsic properties of zirconia can be found by surface coating of titanium that we have done, where the substrate temperature was changed, room temperature and 200 degrees Celsius, and there was a change in the wettability of the surface. And we found the tribological behavior of this sample, tribological in terms of coefficient of friction and wear resistance, for which we use this SS ball of diameter 5 millimeter, and we saw that the coefficient of friction for the pristine sample, as it is titanium, was about this. And as we coated with room temperature and 200 degree, for 200 degree, we have seen the coefficient of friction was very less, up to 1500 cycle, and there was an increase in the coefficient of friction at the end. So the wear rate reduced in this case. SCM image of those trace areas shows that the groups where there debris formation, and EDS results shows the presence of oxygen. So the main the wear was abrasive, adhesive, and oxidation wear. So the zirconia, the hardness of the zirconia was the important, and that reduced the wear resistance of the sample. The last slide is on antibacterial behavior. We have tested the bacteria addition on those samples. This is for pristine sample, and this is for samples coated at 200 degrees. Here we can see that the addition of bacteria and coating colony formation was very less on S200, and the number of dead bacteria was more. This we can clearly see in the merge image. Here the image is still green.
Dr. Kedia, you'll have to conclude soon. Huh?
Okay, so this here again we say that the bacterial infection was less on zirconia coated sample. So finally, I can say that the picosecond pulse laser induced microstructure improved the osseointegration of titanium, and the PLD of zirconia improved wear resistance and improved the wear resistance and antibacterial performance of titanium. So finally, I would like to acknowledge GDBTVG, LLPTD, and ILLS for their direct support and encouragement. I would like to give my special thanks to Dr. Sucharita Sinha, who has started this work in the group, and all others for their contribution and technical support. Thank you.
Thank you. Thank you very much, Dr. Sunita Kedia, for this wonderful presentation, and very interesting too. So now it is open for questions and discussion. Anyone wants to ask any question?
Yeah. Hello.
Yes.
Yeah, Dr. Kedia, I would like to congratulate you on a very fine piece of presentation as well as very fine piece of work. These bacterial work that you are currently doing, these are mostly in vitro studies, or you have moved to?
I am a physicist. I don't.
I know you are a physicist. Because
I don't actually manage to handle this bacteria and cells. We are taking help from biodivision. So we are doing.
Okay, fine. Okay, thank you. I'm done.
Any more questions? Dr. Sunita, I wanted to ask you a very simple question. I mean, it's a practical question. Like most of all the implants that I have seen, whether it is for orthopedics, dental, or anywhere in the body, they have very complex surface profiles. They are not at all planar. So how does one, if you want to do laser modification of surfaces, how will you go about doing that? So that equally it is all the portions of this implant is irradiated in the right way,
Yeah. Actually, ma'am, I can say here that there are motorized computer controlled 5-axis stages are available.
Okay.
We we are using XY stage, but we have seen those 5-axis stage where we can rotate the sample in very controlled manner. I know that there are groove, there are curved surface on the actual implant. So we will work on that. We have an idea that we can work with those kind of 5-axis stages for this kind of surfaces. Now we are concentrating only on the flat part so that we can improve all properties of those flat surfaces.
And in case the body rejection takes place, rejection of the implant, I mean, how do you come to know about it? Is only by the inflammation and other infections and things like that, or?
In general, patient get fever because of this inflammation and pain. Pain is another factor which used to be there. And for metallic implants, it takes 8 months just to get integrated. 8 months to 10 months. So in that time, it has to be checked regularly. So every initially in weeks and then 3 months. So after if it is in a folded part of the body where one can, so after 8 months only the patient can open that part. If it is arm or something, after 8 months he or she will open the part. So at that time one can know if it is painful and if it is, and in initial stage there will be fever to the patient. So blood test and everything can be checked.
So if there are no more questions, I would like to invite the next speaker, Dr. Yes.
Can I share my?
Khageswar Sahu. Yeah. So that's very, I think you're going to speak on a very, very interesting biological aspect of antimicrobial phototherapy, a new frontier in fight against antibiotic resistant bacteria and newly emerging infectious microorganisms. So let me introduce you all to Dr. Khageswar Rao, who is from RRCAT Indore. Dr. Sahu joined RRCAT in September 2003 after successful completion of 46th batch of the training school, BARC Mumbai. And since then, he has been actively involved in the development and evaluation of various photonics-based approaches for biomedical diagnosis and therapy. One of his major activities has been investigations on the use of antimicrobial photodynamic therapy, APDT, for inactivation of antibiotic bacteria and newly emerging infectious microorganisms, which can be a potential alternative to antibiotics for management of localized yet life-threatening infections in clinical scenario. He received Professor Ming Chien Kao Award by the editorial board of Laser Therapy Journal in the year 2016 for his contribution, and he has published 18 research articles in peer-reviewed journals and has 43 conference presentations. He has received the poster and oral presentation awards at national and international conferences. The Department of Atomic Energy has conferred upon him the Scientific and Technological Excellence Award 2019 in May 2021. Today, he will be talking about the antimicrobial phototherapy, a new frontier in fight against antibiotic-resistant bacteria and newly emerging infectious microorganisms. So I invite Dr. Khageswar Sahu to make his presentation.
Ma'am, thank you very much for this introduction. So I will now share my PPT. Yes. So is my slide visible?
Yes, it is visible.
Yeah. At the outset, I would like to thank organizers for this opportunity. And I shall be talking today on antimicrobial photodynamic phototherapy, which already ma'am has explained a little bit. But how we shall see how this can be a new frontier in fight against antibiotic resistant bacteria as well as newly emerging infectious microorganisms. This This is a part of our activities, which comes under the umbrella of biophotonics, being carried out by a division, that is Laser Biomedical Application Division at RRCAT. So this picture at the bottom shows why phototherapy is the next frontier in combating antibiotic resistance. This comes as a pioneering work in Boston University webpage. Okay, I would go by this briefly introduce about what is antimicrobial resistance and what are the current alternatives to antibiotics. Then I shall be coming to the part of antimicrobial photodynamic phototherapy. And then what are the studies which we are carrying out at RRCAT, which are on bacterial as well as viral phototherapy. Then our future objectives. Okay. So we are unfortunately in the time of two pandemics, that is what is called as parallel pandemics. One is antimicrobial resistance, which was slowly consuming the economy as well as the healthcare sector for decades, for at least last 1.5 decades. Then now, unfortunately, we have been devastated by COVID-19. So there is now the latest thing is that they both are linked. Like this COVID-19 pandemic, it seems to will be contributing to antibacterial resistance. This current pandemic will go away, no doubt, but it will contribute to antimicrobial resistance. Opinion is divided, but there is statistics that at least there will be more 1 lakh more death per year, at least in 2020 and 2021, because of COVID-19 in antimicrobial resistance. So what is actually antimicrobial resistance? So see, antibiotics work on bacteria, and then how they work. We can see here when there is no antibiotic, bacteria are dividing and they are happily proliferating. So a common knowledge, if you look at internet, it will say that before antibiotics, 1 out of every 10 infection that happened because of a scrap, that person had to undergo limb amputation. The antibiotics changed all the scenario. Antibiotics lead to rapid cell death of bacteria in a time scale which is clinically suitable. And then what happens with antimicrobial resistance? As the cartoon here shows that when we take antibiotics, some of the bacteria will die. Then yet some of the bacteria, because of some changes, they will thrive, and then they will contribute to further proliferation. So now to go a little bit deeper, how antimicrobial resistance is getting generated. These are the 3 driving factors. Well, first is indiscriminate use or misuse of antibiotics. Then broad spectrum antibacterial use, antibacterial drug use. For example, when we go to a clinician for any kind of thing, for example, in COVID-19, even if 80% of the cases, there were no bacterial co-infection, but still almost all the COVID-19 subjects are being treated with antibiotics. We know antiviral drugs only work on viral diseases. Antibacterial drugs do not work, but still these are being given. Then another contributing factor is spuriated and adulterated antimicrobial compounds. This is a big problem now. That these lead to selection pressure on bacterial population, and this causes some kind of modifications which can be reduced influx, reduced efflux, and drug modification, drug inactivation, and target modification. Like this is the latest. Like the target where antibiotics was working will be modified by the bacteria. So the other thing is that these antibiotic resistant bacteria, they can transfer their antibiotic resistant property to another pathogen by a phenomenon, horizontal gene transfer, leading to generation of another resistant strain. So that is really the problematic situation. So if you see the timeline of antibiotics and AMR, then this is just like kind of a cat and mouse game. Just for example, in 1920, penicillin was discovered by Professor Fleming, but in 1943, resistance against penicillin was discovered. Then cephalosporins came in around 1950. Within 5 or 10 years, resistance to cephalosporins were detected. And then the subsequent decades saw that there is increased instances of antibiotic resistance, and at the same time, there is a void of discovery of antibiotics. That is because now big pharma is not investing much on antibiotics, particularly on therapeutic aspects. They are more more into kind of there are more other complications. but this has led us in a situation where we don't have alternative antibiotics. Now the situation is that there are no antibiotics left against which resistant bacteria are not found. That means we are in a difficult situation altogether. So some investigational alternatives are being explored. One of them is bacteriophage therapy. This is nothing but a virus which can kill a bacteria. But this is again investigational, not foolproof. And there are other two modalities which are coming up. One is efflux inhibitors, because these inhibitors, they would do not allow the bacteria to throw out the antibiotics. But again, bacteria have found a way to modify their target so that efflux inhibitor also would not work. So this is another pathway is that antimicrobial peptides. Our defense mechanism is so that our immune cells produce antimicrobial peptides to kill the bacterial population or the pathogens. That is why they can easily, we can get easily cured of some small infections without antibiotics even. The mechanism is that antibacterial peptides, they work through pore formation mostly, but it has been reported that even against antimicrobial peptides, resistance can be generated, mostly because these three investigational therapies, even if they are not in clinical stage, they work on single targets. So resistance generation is easy. That is why altogether totally different novel approaches have to be thought of. And again, we are in a no action today, no cure tomorrow. Therefore, there is a prediction that in 2050, antimicrobial resistance will contribute to the most death in the world, even more than cancer and diabetes. And in India is in addition to being called the diabetic capital, it is now being termed as the AMR capital of the world. So we have to take up these problems. Government of India has rightly taken up this project in a major scale. They have launched the mission AMR in 2018, and many works are being done. So our journey is towards that. It is antimicrobial phototherapy. So phototherapy has those advantages like selectivity. Then these are non-destructive, non-invasive, because visible light and all, there are no safety concerns as such. And this phototherapy can be induced by various modalities like by ultraviolet and visible light. So the first pioneering work in this field was done by Professor Niels Finsen, who before the antibiotics came, he was treating tuberculosis, that is lupus vulgaris, that is a local of the skin, and he got Nobel Prize in 1903 for this. But the advent of antibiotics really stopped the phototherapy work. And when again antibiotic resistance is coming up, so phototherapy is revived. So during Spanish flu in 1918, phototherapy was found to be the most effective cure for Spanish flu. So in the line with that, RRCAT has a history of phototherapy. Our previous studies with collaborators from clinics have shown that nitrogen laser can be used to cure drug-resistant TB infections, and that was the journey that was taken 2 decades ago. So now our contribution in the latest decades is on antimicrobial photodynamic therapy. So what is this? If you look at antimicrobial photodynamic therapy, this is nothing but combination of two factors. One is a drug, and which is a photoactivable drug, that is a photosensitizer, along with a light of specific wavelength. And this combination leads to some kind of photochemical reactions leading to production of reactive oxygen species, which can damage all the targets in pathogens, multiple targets at a time, and also they can degrade their toxins, and also they can degrade their biofilms. Today in the morning, we were listening to a lecture on biofouling. Biofilms are a bigger problem in biofouling, and they are even bigger problem in hospital infections. So why these antibiotic resistant organisms cannot outtreat APDT? That is because APDT has several targets. They just compared to antibiotics, which has one target at a time, or maybe antiseptics, which have mostly two targets at a time, or 2 or 3 targets. APDT has several targets. The portions which are highlighted in pink are actually the contributions from RRCAT that we have contributed. The portions highlighted in blue are also contributions from RRCAT, but they have also been contributed by previous studies. So it's a summary of the previous studies of our CAT that what I'm going to present is that we started our journey with in vitro studies in 2008. My colleagues were doing that. Then when I came into, when my involvement started, we moved into in vivo studies on several animal models. Then 2019 onwards, we are moving towards some kind of clinical translation and making some devices or something. And in 2020, realizing that this technology has for many applications for SARS-CoV-2 COVID-19, we have also started some. So let's come to what we have been doing. We have started with in vitro, and then in vivo, we have established some kind of animal infection, wound infection models, and we have been monitoring those infections using in-house developed technologies on biophotonics-based techniques such as optical spectroscopy, optical imaging, along with histological and biochemical parameters. And then after APDT, also we're using the same technologies to monitor the healing response. So as I told earlier, the photosensitizer is the crucial part. So we have been using several photosensitizers. The parameters which are of important concern are important for these applications is that the photosensitizers should have high triplet yield. This should be cationic, amphiphilic, and they should have absorption in red or far infrared region, because when you are talking of visible light, there should be minimum some amount of penetration depth, because otherwise the drugs will not be activated. So we have been working on another drug which is a chlorophyll derivatives, but it is an anionic drug. So we have conjugated it with a cationic peptide to make it a cationic positively charged, so that they can bind with the bacterial membrane, because the outside of the bacterial membrane is predominantly negative with respect to the inside of it. So after choosing the photosensitizers, we move to in vitro characterization of those photosensitizers. Our studies have shown that even in case of both the photosensitizers that we have chosen, one is chlorophyll derivative and another is methylene 2, we are observing 3 to 4 log reduction in bacterial survival loss. So this is an important criteria, because any antibacterial therapy has to have at least 3-4 log reduction, that is 99.99% of reduction in survival loss. So then we have been characterizing the effect of these therapeutic procedures on biofilms. Biofilms are actually important problems in bio scenario also. So our AFM studies have shown that this FPTT not only acts on the bacterial wall, bacterial membrane, it just causes flattening of the bacterial cells immediately after the treatment. It also damages any other parts like flagella, which are also important for infection. So it is a kind of a demonstration that is multiple sites of damage. So then we moved on to wound infection studies. So we started with Pseudomonas aeruginosa, which is actually a cause of morbidity and mortality in wounds, bones, and surgical site infections in immunocompromised individuals. Our results, like as I'm showing here, just show that compared to untreated cases, in the treated ones, these are the treated ones, the bacterial load, this is the bacterial load, has come down by around 95 to 99%. These are animal model studies. And in addition to that, APDT is causing hyper attenuation of the hyperinflammation. I know in COVID-19 pandemic, everybody now is well versed of cytokine storm. Cytokine storm is nothing but overwhelming response of inflammatory cytokines. So in infection also, cytokines are produced in excess quantity, more than what is required. They rather cause more damage than the bacteria or the pathogens itself. So in addition to antibiotic treatment, anti-inflammatory drugs are also given in severe infections. So APDT is also causing, there is a decrease in inflammatory cytokines after APDT treatment. For example, these are the uninfected group of animals, wounds, where some level of biomarkers are there, inflammatory biomarkers. In infection, these are going up, and in PDT, they are again coming down. These are on day 2 after the treatment, and on day 5 also, inflammatory cytokines again going up because without treatment group. But in the treatment group, you can see then they have come down. So this modulation of inflammatory response is actually the first and only contribution from RRCAT in this field. So that was given the award by this journal. And then this is the effect of APDT on healing of Pseudomonas aeruginosa infected wounds, as shown in the picture. The APDT is promoting healing because it is killing the bacteria and also additionally generating some response. This is the uninfected wound histology. This is, see the blue stains are there. This is the collagen, and in the infected you don't see any collagen. In the infected plus PDT you see some collagen. So more towards like normal state of recovery. So another bacteria we have chosen is MRSA. It is called a superbug. So methicillin-resistant Staphylococcus aureus is causing havoc in particularly in diabetic foot ulcers. it is leading to amputation, sepsis, and mortality. So that's why we have chosen this model. This is an animal model study. Again, in MRS infected mice, wounds of mice, also we see that this is the PDT group. This is uninfected. This is the PDT infected without any treatment. This is the PDT group. Again, there is healing response is generated. So these are some biomarkers. These biomarkers are again higher at wounds in the infected group, and in the PDT group, that is a PDT group, they have come down, showing that the inflammatory response have also gone down in addition to bacteria. So APDT is also causing collagen restoration. So collagen restoration is the final phase of wound healing, and it is necessary because the original strength of tissue will not recover unless collagen is restored. So we have measured retardance, and we have carried out optical coherence tomography to measure the in vivo response of wound healing. And optical coherence tomography is a fine tool which can show edematic response, inflammatory response in wounds, and not only in wounds, in vivo, in cancer diagnosis also this can be very much helpful, and are being used. And in ophthalmology, these are very much more applications. But we have seen that this retardance measured by OCT and the biomarker of collagen restoration, that is hydroxychloroquine, they have a good correlation. So for example, here in uninfected wound, what we can see is that this is the level of hydroxychloroquine and retardance in the PDT group. These are more towards the uninfected group, and in the infected and without any treatment, these are much lower. So these are suggestive of that collagen restoration is happening. Then we moved on to diabetic animal models, because diabetes is a serious problem, and India is the diabetic capital of the world. And this MRSA infection is more problematic in diabetic foot ulcers. For example, if there is diabetic foot ulcer infection with MRSA, then there is at least some chance, 20 to 25% chance that there will be an infection and there is amputation. And once there is amputation, the 5-year mortality rate is 50%. So our results have shown that in mouse wounds of diabetic mouse infected with MRSA, there is high load of bacteria. Even the bacteria, the amount of bacteria we have applied on the wound, on day 2, we see that bacteria number has increased. That was expected, because in diabetic animal models, just like diabetic individuals, immunity has gone down. So bacteria are able to proliferate. But immediately after PDT, this is the day 2. On day 2 we gave PDT, there is bacterial level has gone down. But then we are observing some regrowth. And then we found out that the single high fluence of light, light fluence is very crucial parameter in PDT, and this may have caused some host inflammatory cell damage. And in fact, we found out that also. For example, when we measured the inflammatory cell content at the wound, we found out compared to untreated wounds in the single PDT group, which has high fluence, the inflammatory cell content has gone down. But in multiple PDT, which was given using low fluence at repeated intervals of 24 hours for 3 days, the inflammatory cell content has gone down. And this is the bacterial load, where we can see that bacterial load in infected untreated group is this much. So for example, 4 into 10 to the 8 CFE per ml and per gram per wound actually. And in the single PDT group, this has gone down to some level. Multiple, it has gone down to again much reduction. This is the silver nitrate treatment group. We kept this as a as a control, because in clinical situation, silver nitrate is used for treatment of even infections and all. So we kept that as a control. So as we can see that compared to silver nitrate also, this APDT is more effective. Then we moved on to study what is the effect of this APDT on angiogenesis and healing of wounds of mice. That is because in diabetes, this angiogenesis, that is the ability to form new capillaries, is much reduced. That is what is the predominant factors why you see ulcers do not heal in diabetic individuals. So any treatment efficacy or any treatment modality has to really in addition to killing the pathogens, it has to also improve wound healing. So angiogenesis has to be promoted. That is why growth factors and everything are given. But growth factors are very costly and they require repeated treatment. And also, these chronic ulcers have a tendency that they have high level of protein degrading enzymes. So growth factors are also not effective. So alternative therapeutics are being tried out. So these results, our results actually show that APDT, in addition to causing decrease in inflammation as well as decrease in bacterial load, is promoting angiogenesis. This VEGF is actually a growth factor, vascular endothelial growth factor for angiogenesis. So as you can see, this is the uninfected wounds. This is at this level, and these are non-diabetic animals, wounds of non-diabetic animals. These are diabetic animals where the VEGF level has gone down, as it was expected. Infection has caused a little bit more decrease, because infection causes destruction of the endothelial cells, and infected PDT, which were given for multiple times, it has, that is infected PDT3 group, it has a more amount of VEGF. So also compared to silver nitrate, VEGF level in PDT group is much higher. This is a group we have chosen, that is, we use something, an inhibitor, which for a compound which is formed during diabetes. In diabetes, sugars are added to the molecules. That is called non-enzymatic addition of sugars to molecules. And this is called advanced glycated end product formation. And that is one of the major complications in diabetes also. So what we did, we took an inhibitor for those glycated end product formation. That is because this is being used also for inhibiting diabetic complications. So, but these do not have antibacterial property. So that's why our two more controls, and one is this green one, which is in silver nitrate group, and the purple one, the violet, this one is the AG group. So okay, now we moved on to another study where we saw that photobiomodulation therapy, I mean the light without any drug, can also lead to improved healing of therapeutic ulcers. Okay, now that is one part of work was antibacterial therapy, and this is antiviral photodynamic therapy. Like antibacterial therapy, this light plus drug combination also can kill virus. That, as I am showing here, the several targets can be destructed at the same time. Once ROS are generated because of PDT, then viral surface protein, their proteases, membrane lipid protein, and all are degraded, leading to virus inactivation. So we carried out a study to explore the efficacy of SARS-CoV-2 photoinactivation using PDT. This was carried out in Employees State Insurance Corporation Medical College, Hyderabad, because they have the BSL-3 facility, we do not have. And we carried out this APDT work there, and we have found by RT-PCR analysis that CT value, that is the cycle threshold value, compared to untreated control, because of PDT at different influences, the CT value is increasing more than 35. This 35 CT value is termed as the negative. When CT value is at 35, the samples are termed negative. So that is some indication that APDT can cause inactivation of virus. So another aspect of our work is UVC. So ultraviolet C also can inactivate the virus. So this is being used, being promoted to inactivate virus on inorganic surfaces. So we have developed a wide area disinfection device that is called Nilvasmi, and it is now available on DA website also. So we conducted this study in ESIC Medical College. Samples were these viral transport medium samples containing virus were spared on different inorganic samples, plastic, glass, cloth, and then they were exposed to Nilvasmi, that is ultraviolet C 254 nanometer, and RT-PCR was conducted. And RT-PCR values show that compared to unirritated ones, ultraviolet C rated ones have CT value much higher, and they have turned negative. So this is the cartoon showing that the virus was sitting pretty happy. You gave Nilvasmi irritation, virus is now killed. The minimum fluence was also determined from our study. So now our future goal. So motivated by all these studies, we want to move into another some slightly higher level where we want to develop some kind of handheld devices for localized photo disinfection of nasal cavity, oral cavity, and also treatment of foot ulcers. So this is a cartoon showing that a spray can be given, and then some LED light can be given to the nasal cavity where bacteria or other pathogens can be inactivated. These are the two pictures I'm showing. These are two models of prototypes that we have come up with in joint collaboration with a industrial partner, and now we are trying to validate these models. And then there are many potential other applications. For example, acne, then fungal infections, BSL, intranasal and bones. So another potential area where these technologies can be used is, can agents of biowarfare can be defeated using light? So that requires BSL-3 facility. We are coming up with that. So my acknowledgement this being, but I would like to sincerely acknowledge Professor Majumdar, Dr. Majumdar, who is the head of our division, and Professor Dr. Nake, S.B. Nake, the director of our group, and the whole LVA team. I have mentioned the name of some colleagues, but not all. But all of them have contributed in some way. Project interns, collaborators, we have clinical collaborators from MGM, Indore, and BSI's Medical College, industry partners, Research India, and then Dr. Cure and Care. So this journey is, moving towards translatable solutions. So hopefully we'll come up with something in near future. And thank you for your patience and opportunity. I'd like to conclude here. Thank you. Thank you.
Thank you very much. Thank you very much, Dr. Sahu, for your this very relevant and very, present day condition when we are going in with all this problem of COVID. I mean, whatever you have suggested, it seems really interesting. And I'm sure, I mean, the instruments that you showed also, the spraying, I mean, the using it for the nasal cavities and things like that. I think it will become like, almost like taking an infrared with the temperatures measurements. So maybe it will happen like that, at every stage. But it's really, really very interesting. And we can, only thing is, if you have to address some parts which are within the body, then, I mean, how do you go about? I mean, do you use a kind of a fiber optic, this thing, just as you do for other heart surgical surgeries and things like that? How do you propose to do that?
Yes, ma'am. In fact, in one of my slides, I showed that this nitrogen laser therapy was being given to the lung cavity. That was very pro, but that has been given from the backside, back. But now fiber optic probes are available. In fact, people are thinking of delivering light to lungs as well as intestinal infections. For example, Helicobacter pylori, madam, you might be also, everybody is aware of, they are causing havoc. These are causing ulcers and all, and antibiotics are not effective on them because they sit in stomach has acidic environment, and the antibiotics and other drugs easily degraded. So people are now thinking of delivering light and the drug solution at the site. And so as you rightly said, it is the fiber optic delivery mode which will be effective. Another potential area is the osteomyelitis, madam. Osteomyelitis is like this bone infections. Their light cannot be directly applied. So there is a fiber optic probe. If it is available, then the fiber optic probe can be inserted to that point. It will be invasive nature, but bone infections are very painful and debilitating. So that much of balance we have to take. And in fact, clinical trials have started. They're using this drug that we are also using for osteomyelitis treatment, and they have shown that this amputation probability gone down severely. I mean, sorry, not severely, significantly after PDT treatment. So as you rightly said, it will be the fiber optic technology which will revolutionize this field.
Thank you very much for your great contribution to society. And if there are any other more questions, I think we have time to take them up for another 7-8 minutes. So if anyone.
Oh, madam, I think we'll have to close the session because the next one is going to start at 2 o'clock.
Okay. So thank you, all of you, Dr. Professor Ranjini, Professor Sunita, and Dr. Khageswar, Sahu, for these wonderful presentations today in this last technical session of the National Laser Symposium. And so we are closing this technical session with that feeling that really we are doing such a lot of work, very interesting work and contribution to society. Thank you very much.
Thank you, ma'am. Thank you.
Thank you very much, Dr. Dhareshwar. And particularly thank you for the last remarks. You really summed it up very well in the nice words. So with this, we end this session and we move on to our next session, which will start at 2 o'clock. So everybody please join us at 2 o'clock. And now we will take a short break for lunch. Please assemble at 2 o'clock. So we will conclude NLS-30. Thank you.
Thank you.
इससे चला है क्या धीरज? वो स्पीच है ना, वो क्या स्पीच, वो पॉइंट्स है, विल कनेक्ट ऑल डॉट्स। दमदार दीजिए। दमदार ही है क्या?
क्या बोल रहे हो, क्या नहीं हुआ? एक्चुअली ये म्यूट कर देना चाहिए। जो भी बात कर रहे हैं ना सब जाएगा।
Good afternoon, everybody. So, as all good things do have to end, I welcome you all again. I'm here to welcome you all again to the concluding session of National Laser Symposium 30. I hope we have had very productive and learning days in the last 3.5 days that we spent. And I hope this learning stays with us and also contributes in our future scientific endeavors. We have with us to preside over this concluding ceremony, Dr. S.V. Nakhe, Director, RRCAT, and also President, Indian Laser Association with us. Welcome, sir. We also have Dr. Piyush Saxena, the Secretary, Indian Laser Association, and Dr. Pankaj Mishra, who is Treasurer, Indian Laser Association with us. All of them are joining online from RRCAT. I welcome you all. We also have Dr. Archana Sharma, Chairperson NLS-30, and of course the organizing members. So I would request Nitin Kavade, my colleague and co-convener of NLS-30, to please summarize the events of the symposium, what we did in the last 3.5 days, and also take this concluding ceremony onward. Thank you.
Thank you, Madam. Good afternoon and welcome to this concluding session. And I will summarize, I will go through the journey. The journey began with symposium when it is announced around mid of the September. Then we start preparing this website, local organization committees, and we have gone through the selection of invited speakers and all the support what we required, that all we started around mid of September or early October, you can say. So we have got that time around 3 months of the time for this preparation, and then we have taken the task, and due to this pandemic situation, this symposium has to be in hybrid mode, and and that was different for us, because earlier we arranged the symposium in person, but this time it was in hybrid mode. So web committee has to be strong. Then our web committee, young, I can say enthusiastic persons, they carry forward this job, and they provide us seamless support to sell the symposium all the way. Okay, so that was the support by web committee and session management committee specifically, because all thing was new for us, and we did manage with four days of symposium. Then precursor to NLS, we conducted 2 ELA courses, tutorial courses, which was benefited by hundreds of students or researchers. Then this symposium began on 19th with keynote address on this extreme science and extreme light. It was enlightenment for us, and this was very informative and elaborative address by Dr. Ravindra Kumar. Thank you, sir. And then it is followed by 25 invited speakers with different sessions and with wide topics, from ultra-fast laser to laser spectroscopy to laser applications to nonlinear optics. So almost all the topics we try to cover through this invited speaker. They share their experiences, they share their knowledge, and it was a really deepen our knowledge through their experiences. Then it was followed by one special evening talk, which was on lightning laser rod. It was a really fantastic talk. It provided us a glimpse, research around world, and how challenging research is going around the world. Then we have covered almost 160 thesis presentation each of the thesis, 150 paper, 160 paper presentation. Each paper presenter will provide 5 minutes of time slot, and almost 900 minutes session we have covered through 6 parallel sessions over 3 days of time. So through this we have provided the opportunity to the paper presenter to say about his or her work. Then I would like to specially mention about this session chairpersons, thesis, and paper evaluator committee for their countless efforts providing and help us to conduct this symposium. Then this time we have provided the symposium in 2 modes, on WebEx, interactive WebEx platform, and other is a video live streaming on the NLS website. So it provides the opportunity, those who cannot log in or who have the problem, they can watch through that website, and this exhibition gallery also provided over there, so that visitors or participants can visit the exhibition gallery, interact with the exhibitors with the platform. And I specifically mention this Deepak Naik, who has provided this web support to us. Then e-proceeding, we have gone through e-proceeding, and e-proceeding is ready with us, and it is uploaded on website. So any participant can download it, use it, and can go through it. Then poster gallery is also available there. So this time website was fantastic, and we have put the effort. So I hope every participant will use it. And I specifically applaud Dr. Vinod Rawat for his support, for providing or for preparing this thesis e-proceeding specifically. With this, I hope next year we'll see with participant or delegates with new ideas and new research topic in presenting in NLS. So now I call upon Dr. Archana Sharma, Chairman, to give an impression about the NLS. Thank you.
Okay. Thank you, Kaudeji, and good afternoon to all. I am thoroughly impressed, if you say what is the impression. When laser was invented, it was told that this is a solution waiting for problems. And in last 4 days, we have heard the quality and quantity of the talks, presenters, and topics which has been covered. It is immensely impressive and very much in-depth and frontal area. As we say, good beginning is half done. So that is how our director, BARC director, TIFR started the procedure, and Professor Ravindra Kumar took the lead in keynote speaker, and it followed till end of our thesis presentation. And I am extremely grateful to all of them, especially young team for web management, IT management, venue, and our seniors, RRF, Dr. Alok Ray, Dr. Vasudev, Sinha Madam, and Vishwanatha sir. They were really our backbone for the working team and guiding to our convener, Dr. Padma, co-convener, Nitinji, secretary, our G. Sridhar, and ML Chaji. And I am not forgetting here our GK Sahu ji, who has done very good catering for all of us. Actually, event is though virtual, but efforts are not less. At every front, only I miss that participant hall is empty. The way things are going on, whenever I am entering the hall, it was always vibrant. Full stage is there. Our chairperson, co-chairperson, they are taking notes, asking questions, and allowing everybody to interact very, very immensely. And I'm really thankful to each and every one of this symposium organizing committee. And I should also thank my co-chairperson, Shri Martinji, who was 4 days he spent here, and he took care of that nothing is getting missed. About these speakers, I want to thank all the speakers from India and abroad who took care of their timings, though it was mismatched with our timing and there, but they took this trouble and shared their work, shared their results, and it is giving direction for our future work. RRCAT, from the day one, they have supported us, and they were the inspiring people when they did first symposium during COVID time. And that is thereafter people started doing more and more conference. So I am thankful to RRCAT team, Director RRCAT, NLS-30. And again, I am grateful to have this program to this such a successful end. So I am thankful to each and everyone. I don't want to miss Ashavari, who was conducting this conference each session, but she never came forward. So, and who are not here, I don't want to miss Mandar, our Dheeraj, Paramjit, and everybody. Thank you so much. I'm really grateful. Thank you. Thank you.
Now I request Director RRCAT, Sri NLS-30, to give an address.
Thank you, Kaudi. I hope I am audible clearly.
Yes, sir, you are audible.
Oh, thank you. So, Dr. Archana Sharma, madam, Padma madam, Martin ji, and Nitin ji, and all other colleagues from BRC. I would like to express my sincere thanks for organizing this symposium in such a short notice, because there was a lot of uncertainties how it can be organized, but the earlier experience has helped to organize it within the limited time and limited resources. Although, as Madam has indicated, that although the symposium is online, but the efforts are almost the same. There is no less efforts are required to organize such type of symposium. Rather, at times the efforts are on higher side itself. Particularly, organizing parallel sessions and getting foreign speakers in time and organizing the sessions and these poster presentations, etc. It becomes quite tough and challenging in this online mode. But nevertheless, it has been organized very well, and a number of papers were presented are great. And I'm told that this year the judges have identified more awardees for the papers, and will be awarding more poster awards this time as compared to the earlier sessions. So this is a special event for this year, and we'll go ahead with this. So all the papers were really good. I'd gone through the abstract book. It is a very nicely arranged and true representation of all our activities. Although before this COVID period, there used to be more number of papers, but I'm sure when we'll start online again in the next year, we'll have more papers and more in-person interactions, and that gives a totally different feeling and impact. But this online mode also gives certain advantages, particularly those who cannot travel or with short notice, they can at least present the papers and they can participate in the symposium. So overall, the symposium has been organized very good. The invited speakers, the choice was excellent, and the sessions were arranged with due care and properly. So once again, I thank organizers, all the participants, and BRNS also for sponsoring this important symposium. So with these small words, and I would like to thank all ELA officials also who have taken a lot of efforts to organize the events properly and to give their best contributions so that the event is organized as per the traditions. Thank you once again, and let us hope we'll have a nice symposium in person next year. Thank you.
Thank you. Thank you, Nake sir, for your praising word. Now I request Dr. Ravindra Kumarji. He is one of the Thesis evaluation committee judge. So for your feedback, I would like to request him on the dais. Please, sir.
Thank you. It's great to be standing here once again in 4 days, second time in 4 days. And thanks for the honor. First I'll say about the thesis evaluations that we heard this morning. I think very good stuff. It's keeping up the tradition of NLS. I think in future probably we should see more and more people coming in. So we were so impressed we decided to give 4 instead of 2. And thanks to ILA for accepting our request. I hope they have. So it's really nice that we can find a lot of enthusiasm for laser applications and lasers, basics of lasers, etc. among the students. So well done. And I just want to take this opportunity to also say that all the people here, I think have done a terrific job. Of course, several people who are down the aisle and also invisible here. So I think it's really, on my behalf, on everyone's behalf, I would like to say congratulations and thank you very much. And I'm sure Dr. Sharma, Dr. Nilaya, everybody can sleep peacefully tonight. They don't have to worry about, is everything going to work okay? Is WebEx okay, the correct platform or not? And it's been very tough. I know the times have been very challenging. And how you maintain, sustain enthusiasm when people are remote and working, not being able to know whether things will go on as planned or not. So much of uncertainty. In spite of all that, if you have done it, it's really remarkable. So personally, NLS has been a journey of growth for so many of us, including me. We have seen lots of them. And it's always been that, I believe NLS is about lasers. So it should be about cavities. So this room is the cavity in which there should be a lot of people, right? And we stimulate each other. So, but unfortunately, things, life throws things at us. And in spite of that, we have managed to sustain ourselves. But hopefully we go back to the old cavity model next year. And where the room is full, everyone is talking excitedly about questioning something and so on. But having said this, I would also like to say that we have found a new way of amplification, which is that now we can reach people much further than, much farther than we have ever reached before. So somebody sitting in Manipur can actually join us. He cannot travel, he or she cannot travel for various reasons. And so the amplification should be kept up next year by WebEx and more. But please, for God's sake, let's all meet in a room, right? So it's a serious wish, not that you're responsible for keeping it this way, but let's all wish that next year we'll be looking at each other, not on the screen, but in person, right? And so thanks very much. It's a great job. And once again, thanks for considering me to be worthy of the keynote address. I hope I have lived up to your expectations. Thanks.
Thank you, sir, for your valuable feedback. Now I request Dr. Alok Ray, sir, to kindly provide your feedback.
Hello. Dr. Archasa Madam, I think Madam is leaving, Martin. Nakheji, and there, Piyush Saxena, and all other, Dr. Padma, and Nitin, Sridhar, Mukesh, and Pankaj. So it was really, when we started, of course I was in the behind scene, as Nitin told, during the September middle, to organize the symposium, because Madam was very much interested to do it. So it was really tough so that they will be able to do a quality symposium. But finally, I am very happy because the symposium is very well managed. The quality of talks and particularly the tempo of the talk, we started with the keynote speaker, Professor Ravindra Kumar. He is so enthusiastic at this age. So with his good scientific background, also with his enthusiasm and good talk, it was inspiring. And everything, I think today thesis management also was a challenge actually, because you have to manage the thesis in the time. So all the judges, they are there, except one Professor Chandravas Narayan. He has a COVID problem, and there are a lot of people are affected, but still, by doing the hybrid mode, they are able to contribute. So I think, as Professor Ravindra Kumar told correctly, that hybrid mode has some lot of advantage, because you can get some people from far also, like a lot of good speakers in the foreign we can get. So that should be continued, but of course we should meet also. That networking, that vibration in the hall also is important. So Nakheji, as you told nicely, that because NLS is continuing for last 30 years, so many things are standardized. So a lot of help comes from all around. So that's why we could arrange it, good quality symposium, and I think that we should continue. So I also thank all the organizers, present organizers here, and ILA also, to do this job again and again. Thank you very much.
Thank you, sir. The feedback session is open to the audience. Can you just put your feedback in chat box? Now I request Dr. Vasudev sir, please provide your feedback for improvement purpose. And specifically, Vasudev sir was chairing the poster evaluation committee. So, Dr. Piyush Saxena ji, you would like to say something about?
Good afternoon.
Good afternoon. At the onset, actually, I wanted to congratulate the symposium organizing committee and the support from the RRCAT. Actually, when this process started, normally I understand that it normally used to start sometime in June, and the symposium used to be in December, January. This time, as I understand, it started quite late. And I was worried that in this COVID time and the short duration, how these people will be able to manage it. No, I can say with a lot of happiness that I think these people had managed it so well, and they really deserve all the praise for that. And in fact, I found that though all the online proceedings, most of the lectures, everything, they were so nicely managed, and they were well in time. And I also contributed in a small way. I was given the responsibility to coordinate the poster evaluations. This time, because since the symposium was online, it cannot be like the earlier time that we ask people to put their posters and the judges can go through, and then finally they can give their judgment. So this time it was designed in such a way that all the people, all the poster participants, they were given times to make their presentation. I am happy to say that earlier, most of the time, symposium, after the symposium, the participant used to say, "Sir, wo judges to hamare poster pe aaye nahi." I mean, many will complain that judges had not come to our poster, how they will judge. So this time, they cannot complain that. Everybody got equal opportunity to present their work, and they were asked questions also. So in the process, I would like to thank, see, all the posters be divided into 6 sessions. Each day we had 2 parallel sessions and 6 committees, and I wanted to thanks all the judges. They had, for their patience, they had gone through the whole process and finally evaluating. I know it is a very difficult job, and in 3 minutes presentation and 2 minute question answer, but still I will say they have done a very good job. And finally, we have decided that in each session, we will ask, we ask the committee that they can give the 3 best posters. And so in total, we have 18 posters. And if they permit me, shall I announce? Achha, okay. So finally, we have decided that this time there will be 18 posters, which has been selected. So with that, I wanted to finish that, and again wanted to thanks the all organizing committee. And actually, I could not attend the inauguration part because I was in isolation at that time. But last 2 days, I really enjoyed the symposium. Thank you very much. Thank you. Yes.
Anything is there in chat box? Now I request Dr. P. Saxena ji to announce this or take over for this award ceremony. Thank you. P. Saxena ji.
Yeah. First of all, I congratulate Dr. Padma, Dr. Kaude, Dr. Shah, and Dr. Sridhar for arranging this NLS-30 in a very successful manner. Starting from the ILA course, and then the posters, invited talks, PhD, we got the very good response in the numbers also, and we have arranged it in a very successful manner under the able guidance of Dr. Archana Sharma and Dr. Nakhe. So I'm thankful for that, Dr. Padma. For the awards, in thesis, there are 15 theses, and for the awards, I will give the mic to Dr. Pankaj Mishra. Hello.
Yeah, I'm audible.
Yes.
Yeah, it is my pleasure to announce the Best Thesis Award during NLS-30. So, as we know, total 15 presentations were done during the thesis presentation session, and all the presentations were excellent. And we can guess how difficult it would have been for the judges to select a few best theses. Thanks to our judges who has selected 4 best theses, and it's my pleasure to announce their name. So the first name is Dr. A.N. Jinu from RRCAT Indore, and his paper ID is 1149. The second name is Dr. B.S. Sathira of ISER Kolkata, and her thesis ID is 1122. Third award goes to Dr. Abhishek Chatterjee of RRCAT Indore, and his paper ID is 1096. And fourth award goes to Nagaraju Gothikonda of University of Hyderabad, and his thesis ID is 1018. So we congratulate all the thesis awardees for their presentation, and the amount of the award is sponsored by Laser Spectra Services, Bangalore. Thank you all.
Thanks, Dr. Pankaj Mishra. Now we will go for the poster awards. This poster awards are sponsored by Laser Sciences Mumbai. I invite again Dr. Vasudev to announce poster awards. Dr. Vasudev.
Thank you, Dr. Saxena. See, as I said earlier, that we had 6 committees, and each committee we asked them to give 3 names. So total we have 18 posters which has been selected. We don't want to make any distinction whatever names they had given. So I will be reading these posters one by one, and not in the order of their merit. All are equal. And so I start with the first one. The first one is that poster identity number I should tell. CP0719, effect of laser remelting on the microstructure of high entropy alloys. P. Chakravarti et al., Material Science Division, BARC, Mumbai. The next one, CP0716, thin photonic crystal templates with plasmonic nanoparticles for trace molecule detection using surface-enhanced Raman spectroscopy, Saranya Narayanan, Advanced Center of Research in High Energy Materials, University of Hyderabad. The next one, CP075, photosensitizer immobilized on aluminum hydroxide microparticles for photodynamics inactivation of bacteria and water disinfection, Alok Dubey, RRCAT. At all. So I am just telling the first name. I mean, there are other authors are there, so I'm not reading all of them. The next one, CP0602, quasi-periodic silver nanostructure achieved with ultra-fast vessel beams evaluations for real-time sensing of explosives. Mr. Banerjee et al., Advanced Center of Research in High Energy Materials, University of Hyderabad. The next one, CP0102, dual pumped CR forest trite laser with enhanced design efficiency, Shiva Sahu, Beam Technology Division, BRC. The next one, CP0113, all Gilbert, not able to read any. Q-switched ytterbium doped laser using fiber optics ring resonator, P.K. Gupta et al., Laser Technology Division, RRCAT. CP0317, fabrication and testing of TSB-PMM composite elements for X-ray imaging at Indus 2, Saranjit Devanath et al., RRCAT. Next, CP0308, fast detection of refractive index inhomogeneities in unpolished neodymium doped phosphate glass slabs using indexed matched liquid by Sicilian techniques. Sanjeev Kumar Tiwari, Laser Technology Division, RRCAT. The next one, CP0315, ultra-sensitive temperature photon sensing using aluminum silicon biomaterials cantilevers. M. Raghu Ramaiya, Surface and Nanoscience Division, IGCAR. Next one, CP0920, 3-step, 3-color selective photoionization of natural ytterbium for enrichment of ytterbium-168, Deepthi Veswal and all group, Advanced Laser Tunable Application Facility, BTTG, BRC. CP0903, atomic fountain of rubidium atom with moving molasses, Surindra Singh et al., Physics Application Section, RRCAT. CP0926, measurement of isotope shift of samarium by 2-color 3-step photoionization techniques, Atula Charan Sahu et al., BTTG, BRC. The next one, CP0513, proton radiography of microstructure and laser-produced plasma flame, S. Bagchi et al., Laser Plasma Division, RRCAT, Indore. CP0403 CPT resonance frequency shift in RB neon vapor cell for application in atomic clock, Jamir Maya Katha. UR Rao Satellite Center, ISRO, Bengaluru. And some co-authors are from BRC, Mumbai. The next one, CP0404, magnetic micro-trapping laser-cooled RB atoms using gold jet wire trap on atom chip. Vivek Singh et al., laser application section, RRCAT, Indore. CP0802, design and development of an automated control system for CO2 laser-assisted tritium-filled glass tube cutting and sealing of Brit. Rajiv Kumar Yadav et al., Material Processing Division, RRCAT, Indore. CP11-1, high voltage picosecond pulse generation by an avalanche transfer stack on microstrip PCB, ML Sharma, Laser Technology Division, RRCAT, Indore. The last one, CP0807, synchronized triggering of multiple spark gaps using optical pulse laser beam, Ritu Agrawal et al., Accelerator and Pulse Power Division, BRC, Mumbai. So with this, I have come to the end of this. Thank you very much.
Thank you. Over to Piyush ji.
Again, I congratulate all the awardees for the posters and the thesis. Thanks again for your cooperation.
Thank you.
Thank you.
Thank you, sir.
I would like to congratulate all the awardees and their co-workers, and again, more importantly, all the judges who have taken painstaking efforts to be patient and be very attentive and going critically through the presentations, and of course the thesis thank again at this moment, because going through the thesis is a really tough task and there were so many of them. So I once again congratulate all and thank the evaluator and organizer. Thank you.
Thank you, sir, for your encouraging word. The list of best thesis and best poster will be shortly uploaded on NLS website, and I think it will be uploaded on this ELA website also. So you can go through that list. Okay. Now, any feedback is there? Mike. There are no more feedback. Now I call upon Secretary NLS-30, Dr. Sridhar, for a vote of thanks.
Good afternoon. In the last 4 days, we have witnessed a vibrant atmosphere created by NLS-30. Because of this NLS-30, this vibrant atmosphere, in order to make this NLS-30 successful, there are many organizations and many volunteers are involved in this. It is now time to thank them, one and all. The foremost, we like to thank Dr. K.N. Vyas and Dr. A.K. Mohanty. Dr. K.N. Vyas, Chairman, Atomic Energy Commission, Dr. A.K. Mohanty, Director, Baba Atomic Research Center, for approving or allowing us to conduct the symposium in BARC and facilitating us. And next, we like to thank Director BTDG, Dr. Archana Sharma, and Head LNPD, Dr. Martin Mascarenas. For day-to-day, they are also playing the another role of chairman and co-chairman of this symposium. They were meticulously following us to day-to-day the progress of the NLS symposium, and each committee they are following closely and make it guiding us to successful completion of this this event. And then we like to thank TSC and TSC for MA clearance, for providing MA clearance. And we like to thank BRNS for providing the financial assistance for this nasal laser symposium. And we like to thank DCACM and Securities for allowing us to providing this DA Convention Center, where we are able to conduct very nicely. And then security for allowing the movement of persons and materials in and out of the BRC. And foremost thank is this laser community. We could able to conduct, as somebody was telling, that laser symposium have a format is well established. So we have a NAC, National Advisory Committee, and Scientific Ordinance Committee, and ELA participation. So this, because of their guidance, NAC and SOC, we thank them for selecting the speakers, invited speakers. We have been spoiled with choices. We have got a lot of invited speakers list. It was very difficult for us to go through and find out. Finally, we could able to get the list of invited speakers with the help of SAC. And I like to thank special mention to Dr. Ravindra Kumar, who was he was proposing a theme of that lasers for green earth. We could not end up in lasers for green earth, but we could go for lasers for safe earth. So he could organize a special evening talk towards the lasers for safe earth. And I also thank Scientific Organizing Committee. Scientific Organizing Committee for reviewing the papers and selecting the reviewers. That's a meticulously that has been done. We have received 160 papers and that has been gone through individual papers and reviewed properly. We like to thank ELA, Indian Laser Association. With their able support, we could able to conduct this symposium very nicely, along with the ELA courses, the 2 days ELA courses. And I thank Sri Naki, Dr. Naki, and Dr. Piyush Saxena and Mishra ji for your able support. Without this, it would have not been possible to conduct these ELA courses and the smooth conduct of the laser symposium. Thank you, Nitin. And then we also thank the poster evaluation committee, Dr. Vasudev, and Thesis evaluation committee, chaired by Dr. Alok Ray. We could able to do efficiently that evaluation of the posters, and I know it is very difficult for posters, 160 posters presenting in 3 days, 2 parallel sessions. We thought it will be a very big task. We will not be able to do it, but somehow that we could able to manage with the help of local organizing committee. I'll come to that next this one. So we thank Dr. Vasudev, Dr. Alok Ray for their support in evaluating the thesis and evaluating the poster committee. Now I'm coming to this local organizing committee. See, behind the scenes, there are so many people are working on that, which we are sitting in the stage. You only see us, but there are so many people are sitting on this thing. So there are so many subcommittees. They could be able to produce fantastic results. We had a scientific committee, and special thanks to Dr. S.D. Nakate for guiding us in evaluating the papers. And publications, Vinod Singh Rawat and his team, they could able to produce, they could able to prepare the abstract book, and now they are working on the e-proceedings. And registration committee, Srimati Anupama and her team, effortlessly they were working, and we don't know what they have done and there, and now the jobs have been neatly done. And then catering committee is very important, because even though we are seeing it's online mode, but here in this hall there are 50 people are sitting here. So in order to conduct this symposium, we need energy. So food is important. Okay. So this catering committee has done a fantastic job feeding us and then giving us energy to conduct this 4 days. We don't know how did the 4 days went. And venue management committee, we thank venue management committee, and special thanks to all. And session management committee, Dr. Asavri and team, they could share our load. We don't need to bother about that session, how to conduct and other things. They could manage it. And four most important things, as it is online, the more load comes on the web committee and web management committee and IT committee. The young 20 volunteers and dynamic people are there under Mandar Joshi, Mukesh Shah. They could be able to do seamlessly. We thought that this online we'll be having a lot of glitches and fear factors were there. Somehow they could be able to make it as if it was almost, it's not exactly physical, but the transitions were very smooth, so we could not feel that any glitches. There are some here and there, but you can say that the confidence level of 98% was through. So thanks to the web management committee and Session Management Committee, and one and all, everyone. So if I miss anyone, it is my poor memory, nothing else. So everyone has contributed, directly or indirectly. And then, yeah, that's, see, my memory has been rekindled. So one of the important transport committee, Dr. Paramjit and his team, they have done that excellent service, even though their load is less in this time, but they could do the extra work on web management. So that is what the involvement of the volunteers. In physical mode, the transport committee would have had a lot of load. Now they know that load is little less than they contributed towards web management, where the requirement is, manpower is more, so they could able to contribute in there. So I wish one and all that we could able to, with the teamwork, it's a teamwork, we could able to pull that in a short time. And one last thing is, we try to accommodate the people. Last time they tried to include the process. We could able to do whatever best we can do. If any lapses are there from our side, inadvertently, we're sorry for that. Hope you enjoyed this NLS-30. We thank you, one and all. Thank you.
Thank you, Sridhar. With this, we declare NLS-30 is over. We'll see you next time in next NLS with fresh mind. Thank you. Bye-bye.
Thank you.
पीछे बैकग्राउंड छोड़ दो मैडम,
ये बंद हो गया, ये बंद हो गया फोन आपका। फोटो लिया आपकी टाइम तक लिए, फोटो के बाद बंद हो गया।